If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. Why space travel is humanity's ultimate frontier. Space travel represents the pinnacle of human curiosity, ambition, and ingenuity. The mere concept of venturing beyond Earth evokes a sense of awe, sparking questions about the universe and our place within it. But why does this exploration matter? Why is space travel considered humanity's ultimate frontier? To answer these questions, we must delve into our innate desire to discover, the scientific breakthroughs that make it possible, and the monumental challenges that lie ahead. From the earliest days of stargazing, humans have been captivated by the mysteries of the cosmos. Ancient civilizations used the stars as guides, charting their movements to predict seasons, navigate oceans, and create mythologies. Fast forward to the modern era, and this fascination has transformed into a quest to physically traverse the void. The shift from observation to exploration required an understanding of physics, our most potent tool for unraveling the universe's secrets. The physics of space travel begins with one simple but profound fact. Earth's gravity is a formidable obstacle. Without mastering the forces that bind us to our home planet, leaving it would remain a dream. The first successful rockets demonstrated humanity's ability to manipulate physical principles to overcome gravity's pull. Newton's laws of motion became the foundation of rocketry, and the space age was born. But space travel isn't merely about leaving Earth. It's about expanding the realm of human existence. In the vastness of space lies the potential for knowledge, survival, and resources. Consider this. Earth, as abundant as it seems, has finite resources and an expiration date. The inevitability of cosmic or environmental catastrophes compels us to seek alternatives. Space, with its boundless possibilities, offers a solution. The challenges of space travel are immense, and physics is at the heart of every solution. How do we sustain life in an environment hostile to it? How do we build machines capable of traversing billions of kilometers? How do we communicate across the unimaginable distances of interstellar space? Each question pushes the boundaries of science and engineering, demanding new technologies and deeper understanding. Moreover, the pursuit of space travel has already brought tangible benefits. Satellite technology, a direct result of our efforts to explore space, has revolutionized communication, weather prediction, and global navigation. The principles of orbital mechanics, once an abstract concept, now govern systems that connect the modern world. In solving the problems of space travel, we've inadvertently improved life on Earth. But there's more to this frontier than practicality. Space travel embodies the human spirit of exploration. Just as our ancestors crossed oceans and continents, we now stand on the brink of interplanetary and even interstellar voyages. Each step into the cosmos is a testament to our resilience, creativity, and determination to transcend limits. As we look to the future, the stakes are higher than ever. Space travel is no longer the exclusive domain of superpowers or government agencies. Private companies and international collaborations are redefining what's possible. The idea of colonizing Mars, mining asteroids, or even sending humans beyond the solar system is no longer science fiction, but a tangible goal. The ultimate frontier of space travel is more than a scientific challenge. It's a philosophical journey. What will we find as we push farther into the unknown? Will we discover life elsewhere, proving that we're not alone? Or will we uncover the profound silence of a universe waiting for us to fill it with meaning? These questions drive humanity forward, uniting physics, curiosity, and hope in the quest for answers. And so, as rockets roar into the skies and spacecraft venture into the void, we are reminded of why space travel matters. It is the pursuit of the infinite, the exploration of the unknown, and the embodiment of what it means to be human. Overcoming gravity, escaping Earth's pull. Every journey into space begins with a monumental challenge: breaking free from Earth's gravitational grasp. Gravity, the invisible force that holds us firmly on the surface of our planet, is one of nature's most powerful and persistent phenomena. Overcoming it is not just an engineering feat, it's a masterclass in applying the laws of physics. How do we escape the pull of a force so strong that it keeps our oceans in place, and the moon locked in orbit? The answer lies in the interplay of motion, energy, and innovation. At the heart of this endeavor is Newton's law of universal gravitation. It explains that every object with mass exerts an attractive force on every other object. Earth, with its massive size, exerts a gravitational force so strong that achieving escape velocity, a speed of about 11.2 kilometers per second, is required to break free. To put that in perspective, it's nearly 40,000 kilometers per hour, faster than any car, train, or plane ever built. This speed isn't just a target, it's a minimum threshold. Falling short of escape velocity means a spacecraft will succumb to gravity's relentless pull, potentially crashing back to Earth or becoming trapped in a decaying orbit. Achieving this velocity requires immense energy, and that's where rockets come into play. Rockets, with their iconic fiery tails, are the quintessential tools for escaping gravity. They operate on the principle of action and reaction, described by Newton's third law of motion. For every action, there is an equal and opposite reaction. As a rocket expels exhaust gases downward at incredible speeds, it propels itself upward. This simple, yet profound principle powers every launch, from the modest beginnings of space exploration to the massive boosters of modern missions. The efficiency of a rocket depends largely on the Tsiolkovsky rocket equation, which calculates the velocity a rocket can achieve based on the mass of its fuel, payload, and exhaust velocity. This equation highlights a major challenge. The more fuel a rocket carries, the heavier it becomes, requiring even more fuel to lift that weight. This feedback loop forces engineers to strike a delicate balance between fuel and payload, optimizing designs to ensure maximum efficiency. Consider the Saturn V, the rocket that carried humans to the moon. It stood 110 meters tall and weighed nearly 3,000 tons at liftoff, with most of that weight being fuel. As it ascended, stage by stage, it shed parts of itself, reducing weight and allowing the remaining stages to accelerate further. This staged approach is a direct application of physics, minimizing mass while maximizing thrust. But fuel isn't the only challenge. The rocket must navigate through Earth's atmosphere, a dense layer of air that adds resistance and generates intense heat. The early moments of a launch are among the most critical, as the rocket's engines work at full power to combat gravity and atmospheric drag simultaneously. The faster the rocket moves, the more friction it encounters, creating temperatures capable of melting steel. Engineers design rockets with heat-resistant materials and streamlined shapes to survive this fiery ascent. Even after reaching space, gravity doesn't disappear, it simply weakens. In low Earth orbit, for example, a spacecraft experiences microgravity, not because it's free from Earth's pull, but because it's perpetually falling around the planet. This state, known as freefall, creates the sensation of weightlessness. To go beyond low Earth orbit, a spacecraft must achieve higher velocities, further defying gravity's influence. The physics of escaping Earth's gravity has shaped the evolution of space travel, pushing the boundaries of technology and engineering. From chemical propulsion systems to innovations like ion drives and reusable rockets, humanity continues to refine its approach to this monumental challenge. Reusability, pioneered by companies like SpaceX, has revolutionized the cost and accessibility of space travel, making the dream of interplanetary exploration more feasible. Why is this fight against gravity so important? Because it's the gateway to the universe. Every mission to the moon, Mars, or beyond begins with the same struggle: the battle to escape the bonds of Earth. Each successful launch is a triumph of physics, a testament to human ingenuity, and a step closer to unlocking the mysteries of the cosmos. The role of orbital mechanics. Once a spacecraft escapes Earth's gravity, its journey is far from over. To travel through the vast expanse of space efficiently and precisely, it must navigate using the principles of orbital mechanics. These principles, derived from centuries of study and observation, govern the motion of objects under the influence of gravity and are the cornerstone of modern space travel. How do spacecraft maneuver in the vacuum of space? And why do they follow such intricate paths to reach their destinations? The answers lie in the elegant and immutable laws of orbital mechanics. At its core, Orbital mechanics is the study of how objects move in orbit around a central body, usually governed by the gravitational pull of that body. The foundation of this field was laid by Johannes Kepler in the early 17th century, whose three laws of planetary motion describe how planets orbit the Sun. Kepler's insights, coupled with Newton's law of gravitation, form the mathematical framework for understanding and predicting orbital paths. The first principle of orbital mechanics is that orbits are not necessarily circular. Most orbits are elliptical, with the central body, such as Earth, the Sun, or another celestial object, occupying one of the foci of the ellipse. This means that a spacecraft's distance from the central body varies as it moves along its orbital path, affecting its speed. When the spacecraft is closer to the central body, at its periapsis, it moves faster. When farther away, at its apoapsis, it slows down. This variation is a direct consequence of the conservation of angular momentum. For spacecraft, this knowledge is critical. Engineers and scientists use it to design transfer orbits, which are specific paths that allow a spacecraft to move efficiently between 2 points. One common example is the Hohmann transfer orbit, a technique that minimizes fuel use by carefully timing the spacecraft's departure and arrival. By firing its engines at the right moment, the spacecraft can transition from one orbit to another with precision, saving valuable resources. But achieving the desired orbit requires more than just escaping Earth's atmosphere. Once a rocket reaches space, it must perform a series of maneuvers to establish its trajectory. This process begins with achieving orbital insertion, where the spacecraft fires its engines to enter a stable orbit around Earth or another celestial body. Without this crucial step, the spacecraft would either escape into deep space or fall back to Earth. Orbital mechanics also explains why launching a spacecraft requires such careful planning. The timing of a launch is meticulously calculated to align with the target's position in space, whether it's the International Space Station, the Moon, or a distant planet. This synchronization ensures that the spacecraft can intercept its destination using the least amount of energy, a principle known as the delta-v budget. Delta-v, or change in velocity, is a measure of how much thrust is needed to alter a spacecraft's path. Every kilogram of fuel expended to achieve delta-v is a precious commodity, so efficiency is paramount. One of the most fascinating aspects of orbital mechanics is the concept of gravity assists, also known as slingshot maneuvers. By flying close to a massive celestial body, such as a planet or moon, a spacecraft can gain or lose speed through gravitational interactions. This technique allows missions to reach distant destinations with minimal fuel consumption, effectively borrowing energy from the gravitational field of the assisting body. Gravity assists have been used in numerous high-profile missions, including Voyager, Cassini, and Juno, enabling them to explore the outer reaches of the solar system. Spacecraft also use orbital mechanics to perform delicate tasks, such as docking with the International Space Station or landing on other planets. These operations require precise calculations to match velocities and trajectories, often involving complex maneuvers like rendezvous burns and braking procedures. The mathematics behind these maneuvers is unforgiving. Even a tiny error can result in mission failure. Understanding orbital mechanics is not just about moving from one point to another. It's about mastering the art of using natural forces to our advantage. By leveraging the gravitational pull of celestial bodies and the conservation of momentum, spacecraft can achieve feats that would otherwise be impossible. This interplay of forces transforms the seemingly chaotic dance of celestial objects into a predictable and navigable system. The practical applications of orbital mechanics extend beyond exploration. Satellites in geostationary orbit, for example, remain fixed above a specific point on Earth, enabling continuous communication and monitoring. Meanwhile, polar orbits allow satellites to scan the entire surface of the planet over time, providing critical data for weather prediction, environmental monitoring, and global navigation systems. Orbital mechanics is both a science and an art, requiring a deep understanding of physics and a creative approach to problem solving. Each mission is a testament to humanity's ability to harness the laws of nature for exploration and discovery. As we look to the future, the principles of orbital mechanics will continue to guide our journey, whether we're landing humans on Mars, mining asteroids, or venturing into the uncharted realms of interstellar space. The rocket equation and its implications. At the heart of space travel lies one of the most elegant and challenging equations in physics, the Tsiolkovsky rocket equation. This formula, a cornerstone of astronautics, describes the relationship between the velocity of a spacecraft, the mass of its fuel, and the efficiency of its propulsion system. It's a deceptively simple equation, yet its implications shape every aspect of rocket design and mission planning. What makes this equation so pivotal, and why does it impose such significant constraints on space exploration? The Tsiolkovsky rocket equation, formulated in the late 19th century by Russian scientist Konstantin Tsiolkovsky, is expressed mathematically as delta V equals VLN, M0 MF, backslash delta V equals V underscore backslash, dot backslash LN backslash left, backslash frac, M underscore 0 underscore backslash right, delta V equals VLN, MF M0, where delta V backslash delta V delta V, the change in velocity needed for the mission, known as delta V. Vev underscore Eve, the effective exhaust velocity of the rocket engine. M0 M underscore 0 M0, the initial mass of the rocket, including fuel. MF underscore FMF, the final mass of the rocket after fuel is expended. At its core, the equation reveals a fundamental truth. To achieve higher velocities, a rocket must either carry more fuel, improve its exhaust velocity, or reduce its payload mass. This relationship is straightforward in principle, but becomes exceedingly complex in practice due to the trade-offs involved. One of the most significant challenges arises from the exponential nature of the equation. To increase a rocket's delta V, the required fuel mass grows exponentially relative to the payload. This phenomenon is often referred to as the tyranny of the rocket equation. For example, doubling the payload might require exponentially more fuel, which in turn increases the rocket's weight, demanding even more fuel to lift the additional mass. This vicious cycle limits how much payload a rocket can carry and how far it can go. To mitigate this, engineers have developed strategies to optimize rocket performance. One common approach is the use of multi-stage rockets, where each stage is jettisoned once its fuel is depleted. By shedding empty tanks and engines, the rocket's mass is significantly reduced, allowing subsequent stages to accelerate more efficiently. This principle was famously employed in the Saturn V rocket, which carried astronauts to the moon during the Apollo missions. Another way to improve delta V is by increasing the exhaust velocity, Vev underscore Eve. This depends on the type of propulsion system used. Traditional chemical rockets, which rely on the combustion of liquid or solid propellants, have relatively low exhaust velocities but produce immense thrust, making them ideal for escaping Earth's gravity. However, for missions requiring sustained acceleration in space, more efficient propulsion systems, such as ion engines, are often preferred. These engines achieve much higher exhaust velocities by using electromagnetic fields to accelerate ions, although they generate far less thrust. The rocket equation also underscores the importance of reducing payload mass. Every kilogram saved in spacecraft design translates to significant fuel savings, which is why engineers strive for lightweight materials and compact systems. Advances in miniaturization, from microprocessors to nanosatellites, have revolutionized the field, enabling missions that were previously inconceivable. Despite these innovations, the rocket equation imposes a hard ceiling on what chemical propulsion can achieve. For interplanetary and interstellar missions, where delta V requirements are immense, alternative propulsion methods are being explored. Concepts like nuclear thermal propulsion, which heats a propellant using a nuclear reactor, offer higher exhaust velocities and greater efficiency. Even more speculative technologies, such as antimatter engines and fusion propulsion, aim to break the barriers imposed by traditional methods. The implications of the rocket equation extend beyond propulsion. It shapes mission trajectories, determining the most efficient paths to reach destinations. Engineers meticulously plan each phase of a mission, from launch to orbital insertion to landing, to minimize fuel consumption and maximize payload capacity. Techniques like gravity assists, discussed in the previous chapter, are direct applications of this principle, leveraging the natural motion of celestial bodies to conserve delta V. The equation also highlights the potential of in situ resource utilization, ISRU. By harvesting resources like water ice from the Moon or Mars and converting it into fuel, future missions could dramatically reduce the amount of fuel that needs to be launched from Earth. This would not only lower costs, but also open the door to more ambitious missions, such as establishing permanent colonies or sending probes to distant stars. In addition to its technical implications, the rocket equation has philosophical significance. It represents the intricate balance between ambition and limitation, between human ingenuity and the immutable laws of nature. Each launch is a testament to our ability to work within these constraints, turning mathematical challenges into triumphs of engineering. The rocket equation reminds us that space travel is a delicate dance with the forces of physics. It challenges us to think creatively, to innovate, and to push the boundaries of what is possible. As humanity ventures farther into the cosmos, the principles embedded in this equation will continue to guide our journey, illuminating the path to the stars. The challenges of relativity in space travel. As we extend our gaze beyond the solar system and envision traveling to distant stars, a profound barrier emerges: the nature of space-time itself. Albert Einstein's theories of relativity, which revolutionized our understanding of the universe, imposed strict limitations on speed, time, and energy. These principles present unique challenges for space travel, particularly for interstellar missions, where distances are measured in light years and time behaves in unexpected ways. How do these relativistic effects shape our exploration of the cosmos, and are there ways to overcome them? Einstein's special theory of relativity introduced a groundbreaking concept: the speed of light in a vacuum, approximately 299,792 kilometers per second, is the ultimate speed limit. Nothing with mass can accelerate to or exceed this velocity because, as an object approaches the speed of light, its relativistic mass increases exponentially, requiring infinite energy to continue accelerating. This limitation fundamentally constrains the speeds at which spacecraft can travel, making journeys to even the closest stars, such as Proxima Centauri, for 0.24 light-years away, a multi-generational endeavor using current technology. The implications of relativity extend beyond speed. Time itself behaves differently at relativistic velocities, a phenomenon known as time dilation. According to special relativity, time passes more slowly for an object in motion relative to a stationary observer. For a spacecraft traveling at a significant fraction of the speed of light, years might pass for the crew, while decades or centuries elapse on Earth. This discrepancy raises profound logistical and philosophical questions. How do we maintain communication with a crew experiencing time at a different rate? What societal implications arise when explorers return to a world that has aged far beyond their own experiences? General relativity, Einstein's theory of gravitation, adds further complexity. It describes how massive objects such as planets, stars, and black holes warp the fabric of space-time, creating gravitational fields. This warping affects not only the motion of celestial bodies but also the passage of time itself, a phenomenon known as gravitational time dilation. In the vicinity of a strong gravitational field, time slows down relative to regions with weaker gravity. These effects, while subtle under earthly conditions, become significant in deep space, particularly near massive objects like black holes or neutron stars. For space travel, navigating these relativistic landscapes requires both precision and creativity. Engineers and scientists must account for time dilation when planning missions, especially for spacecraft traveling at high velocities or operating near intense gravitational fields. The Global Positioning System, GPS, on Earth already provides a small-scale example of this challenge. GPS satellites, which orbit high above the planet, experience weaker gravity and faster orbital speeds than objects on Earth's surface. To ensure accurate positioning, their clocks are adjusted to account for both special and general relativistic effects. The vast distances between stars further complicate interstellar travel. Even at a significant fraction of the speed of light, reaching nearby systems would take decades or centuries. For instance, a spacecraft traveling at 10% of the speed of light would take over 40 years to reach Proxima Centauri. Such missions would require unprecedented advancements in propulsion technology, life support systems, and autonomous navigation. Alternatively, they might depend on multi-generational crews, hibernation technologies, or robotic explorers. Despite these challenges, relativity also offers potential opportunities for space travel. Theoretical concepts such as warp drives and wormholes, inspired by general relativity, suggest ways to circumvent the speed of light limitation. A warp drive, for example, would contract space-time in front of a spacecraft while expanding it behind, effectively allowing the craft to surf through space-time without violating relativistic constraints. Similarly, wormholes, hypothetical shortcuts through space-time, could enable instantaneous travel between distant points. While these ideas remain speculative and face significant scientific and engineering hurdles, they highlight the innovative possibilities that relativity inspires. In the realm of practical space travel, understanding relativistic effects is essential for long-duration missions, especially those involving high speeds or proximity to massive celestial bodies. Precision in navigation, timing, and energy management becomes critical as these missions push the boundaries of current technology. Advanced propulsion systems, such as antimatter engines or laser-powered light sails, must not only achieve higher speeds, but also account for the relativistic impacts on their trajectories and communication systems. Relativity also influences how we think about communication across interstellar distances. Even at the speed of light, messages between Earth and a spacecraft traveling to Proxima Centauri would take over 4 years one way. This delay necessitates autonomous decision-making and artificial intelligence on board the spacecraft, as real-time communication with mission control becomes impossible. Finally, relativity forces us to confront the profound implications of time and distance on human experience. A journey to the stars is not just a technological challenge, but a cultural and existential one. How do we adapt to the idea that explorers might leave Earth never to return, or to find their homeworld transformed beyond recognition? What kind of society would undertake such missions, and how would it sustain the commitment across generations? The challenges of relativity in space travel remind us that the cosmos is not merely a physical frontier, but also an intellectual one. Each obstacle it presents pushes us to think deeper, innovate further, and embrace the mysteries of the universe. As humanity continues to dream of traveling to the stars, the principles of relativity will remain both a guide and a boundary, shaping the future of exploration in ways we are only beginning to understand. Interstellar propulsion methods. The dream of reaching other stars has captivated humanity for generations. However, the vast distances involved, measured in light years, pose an extraordinary challenge for propulsion systems. Current spacecraft technologies are sufficient for exploring our solar system, but interstellar travel demands speeds and efficiencies that far exceed what chemical rockets can achieve. To overcome these hurdles, scientists and engineers are developing a range of advanced propulsion methods, each with unique potential and limitations. What does it take to propel a spacecraft across interstellar distances, and which technologies might unlock this ultimate frontier? Chemical propulsion, the workhorse of modern space exploration, is limited by its reliance on burning fuel to generate thrust. While highly effective for launching payloads from Earth and navigating within our solar system, it's woefully inadequate for interstellar travel. The primary limitation is its low specific impulse, a measure of fuel efficiency. Chemical rockets simply cannot carry enough fuel to achieve the speeds required for such distant journeys. This limitation has spurred the exploration of alternative propulsion methods. One promising technology is nuclear thermal propulsion. This system uses a nuclear reactor to heat a propellant, such as hydrogen, which is then expelled at high velocity to produce thrust. Nuclear thermal engines offer a much higher specific impulse than chemical rockets, enabling faster travel times within the solar system. However, while they could dramatically improve mission efficiency, they still fall short of the requirements for interstellar travel. For missions beyond our solar system, propulsion systems must achieve far greater speeds, often approaching a significant fraction of the speed of light. One such technology under investigation is ion propulsion, which generates thrust by electrically accelerating ions to high velocities. Ion engines, like those used on NASA's Dawn spacecraft, are incredibly fuel efficient and can operate for extended periods. While their low thrust makes them unsuitable for escaping Earth's gravity, they are ideal for gradually accelerating spacecraft in the vacuum of space. However, even ion propulsion would require decades or centuries to reach the nearest stars. An even more advanced concept is nuclear fusion propulsion, which seeks to harness the energy released during the fusion of atomic nuclei. Fusion reactions produce vastly more energy per unit of fuel than chemical or nuclear fission reactions, making them a tantalizing option for interstellar travel. Theoretical designs, such as the fusion-powered Bussard ramjet, propose collecting hydrogen from the interstellar medium and using it as both fuel and reaction mass. While fusion propulsion could potentially achieve speeds up to 10% of the speed of light, significant technical challenges remain, including sustaining controlled fusion reactions and managing immense heat. Another groundbreaking approach is the use of light sails, a concept inspired by the pressure exerted by photons, particles of light. By reflecting sunlight or laser beams off a large, lightweight sail, a spacecraft can achieve continuous acceleration without carrying fuel. The Breakthrough Starshot initiative aims to develop light sail technology capable of propelling small probes to Alpha Centauri, our nearest star system, at speeds of up to 20% of the speed of light. This approach minimizes the need for onboard fuel, but requires powerful lasers and precise targeting over vast distances. Antimatter propulsion represents another frontier in interstellar travel. When matter and antimatter collide, they annihilate each other, releasing energy with unmatched efficiency. A spacecraft powered by antimatter could achieve incredible speeds, potentially approaching relativistic velocities. However, the production and storage of antimatter are prohibitively expensive and technologically complex, limiting its feasibility in the near term. For truly revolutionary advancements, theoretical concepts like warp drives and wormholes come into play. A warp drive, as envisioned in the Alcubierre metric, would involve contracting spacetime in front of a spacecraft while expanding it behind, allowing the craft to move faster than light relative to distant observers without violating Einstein's theory of relativity. Similarly, wormholes could serve as shortcuts through spacetime, connecting distant regions of the universe instantaneously. While these ideas remain speculative, they inspire ongoing research in physics and could one day transform interstellar travel. One critical consideration for all propulsion methods is energy. Interstellar missions require immense amounts of energy, both for propulsion and for maintaining onboard systems during journeys that could span decades or centuries. Solar energy becomes less viable as spacecraft move farther from the sun, necessitating alternatives like nuclear power or onboard energy storage. Advances in energy efficiency and generation will be key to enabling long-duration missions. Interstellar propulsion is not merely a technical challenge. It's a philosophical and logistical one. The vast timescales involved demand new approaches to mission design. Should we aim for crewed missions or robotic probes? Would generation ships, where multiple generations of humans live and die during the journey, be practical or ethical? Or should we focus on faster, smaller probes that can reach distant stars within a human lifetime? Each propulsion method represents a step toward overcoming the immense barriers of interstellar travel. While some technologies are within reach, others remain in the realm of science fiction. Yet, history has shown that today's impossibilities can become tomorrow's achievements. As humanity continues to push the boundaries of exploration, the quest for interstellar propulsion will drive innovation, expand our understanding of physics, and bring us closer to the stars. Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. Surviving the vacuum of space. The vacuum of space is one of the most hostile environments imaginable, an unforgiving expanse where extreme temperatures, cosmic radiation, and the absence of atmospheric pressure present constant threats. Surviving this harsh environment is a monumental challenge, requiring meticulous engineering, innovative materials, and a profound understanding of physics. How do humans and spacecraft endure the vacuum of space? And what technologies make survival possible? Space is defined by its emptiness, devoid of air, water, or any of the essential elements that support life. For humans, this emptiness is lethal. Without atmospheric pressure, bodily fluids would begin to boil at normal body temperature due to the drastic drop in pressure. This phenomenon, known as ebullition, occurs because liquids in the body, such as saliva and blood, vaporize in the vacuum of space. At the same time, the lack of oxygen causes hypoxia, leading to unconsciousness within seconds. Spacecraft and spacesuits are designed to counteract these effects, creating artificial environments that mimic the conditions of Earth. Spacesuits, for example, act as personal spacecraft, providing oxygen, maintaining pressure, and shielding astronauts from radiation and temperature extremes. The layers of a spacesuit include a gas-pressurized inner layer, insulation for temperature control, and an outer shell made of abrasion-resistant materials. Each element is engineered to address a specific challenge posed by the vacuum. One of the most significant threats in space is temperature. Without an atmosphere to regulate heat transfer, temperatures in space can range from hundreds of degrees below freezing in the shadow of a planet to scorching heat in direct sunlight. This thermal variability can destroy electronics, weaken materials, and harm humans. Spacecraft are equipped with thermal control systems, including insulating materials, radiators, and heat pipes, to maintain stable internal temperatures. Spacesuits feature similar systems, using liquid cooling garments to remove excess heat from astronauts' bodies during spacewalks. Cosmic radiation presents another formidable hazard. Unlike Earth, which is shielded by its magnetic field and atmosphere, spacecraft are directly exposed to high-energy particles from the Sun and distant galaxies. These particles, including protons and heavy ions, can damage DNA, increasing the risk of cancer and other health issues. Radiation also poses a risk to spacecraft systems, potentially causing malfunctions or data corruption. To mitigate these risks, spacecraft use shielding materials such as aluminum and polyethylene, which are effective at absorbing radiation. Advanced designs incorporate magnetic fields or electrostatic barriers to deflect high-energy particles. Microgravity, while not a direct consequence of the vacuum, is an inherent feature of the space environment and presents its own challenges. Prolonged exposure to microgravity causes muscle atrophy, bone density loss, and cardiovascular changes in astronauts. These effects result from the lack of gravitational force on the body, which reduces the physical demands on muscles and bones. To counteract these effects, astronauts engage in rigorous exercise regimens, using specialized equipment such as resistance machines and treadmills with harnesses. Research into artificial gravity, such as rotating habitats that create centrifugal force, offers potential solutions for long-term missions. Spacecraft systems are also vulnerable to the vacuum. Without atmospheric pressure, materials can outgas, releasing trapped gases that might contaminate sensitive instruments or obscure optical systems. Lubricants used in machinery can evaporate or degrade, leading to mechanical failures. Engineers address these challenges by selecting materials specifically tested for vacuum conditions and designing systems to operate without traditional lubricants. For example, many spacecraft components use solid lubricants or vacuum-compatible fluids. Communication and power are additional challenges in the vacuum of space. The lack of a breathable atmosphere necessitates closed-loop life support systems, which recycle air and water to sustain human life. These systems must operate flawlessly, as a failure could be catastrophic. Communication relies on electromagnetic waves, which can travel through the vacuum but are limited by the speed of light and require precise targeting to maintain contact with Earth or other spacecraft. Solar panels, the primary power source for most spacecraft, must be designed to withstand radiation and temperature extremes while converting sunlight efficiently. Space debris, ranging from tiny fragments of satellites to larger defunct spacecraft, is a growing concern in Earth's orbit. Traveling at speeds of tens of thousands of kilometers per hour, even a small piece of debris can cause significant damage upon impact. To protect spacecraft, engineers employ shielding, such as multi-layered materials that absorb and dissipate energy from collisions. The Whipple shield, for example, uses multiple layers of thin materials to break apart debris and reduce its kinetic energy before it reaches the main spacecraft structure. The vacuum of space also challenges human psychology. Isolation, confinement, and the inherent dangers of space travel can take a toll on mental health. Astronauts undergo rigorous psychological training and support to prepare for these stresses. Long-duration missions, such as those to Mars, require even more robust psychological support systems, including virtual reality environments and real-time communication with loved ones. Ultimately, surviving the vacuum of space is a testament to human ingenuity. Each piece of technology, from spacesuits to spacecraft, is a carefully crafted solution to an array of interconnected problems. As missions become more ambitious, venturing farther from Earth and for longer durations, the demands on these systems will grow. Research into new materials, closed-loop ecosystems, and radiation shielding will be critical to ensuring survival in the hostile expanse of space. Every mission that succeeds in overcoming the challenges of the vacuum represents a leap forward in our understanding and capability. It is a reminder that, despite the hostility of space, humanity's determination and innovation can carve out a fragile sanctuary, even in the most inhospitable environments. Spacecraft navigation and autonomy. Navigating the vastness of space is a feat of extraordinary precision and complexity. Unlike on Earth, where landmarks and GPS networks provide clear guidance, space offers no such conveniences. Instead, spacecraft rely on advanced technologies and the principles of physics to chart their courses, often over millions or billions of kilometers. How do these vehicles find their way in the endless void? And how is autonomy enabling missions to explore deeper and farther than ever before? At the foundation of spacecraft navigation is an understanding of celestial mechanics. Spacecraft trajectories are governed by the gravitational influence of celestial bodies, from planets to stars. Using these predictable forces, engineers can calculate paths that take advantage of natural motion, minimizing fuel consumption. For instance, a spacecraft might enter a transfer orbit, such as a Hohmann transfer, to efficiently move between planets. These precise calculations rely on Newton's laws of motion and gravitation, as well as corrections derived from Einstein's theory of relativity. Navigation begins before a spacecraft even leaves Earth. Mission planners map out every stage of the journey, accounting for gravitational influences, orbital alignments, and energy requirements. Once in space, the spacecraft must continually verify its position and adjust its trajectory. This is where onboard systems and ground-based support play crucial roles. Ground-based navigation. For decades, spacecraft have relied heavily on ground stations for navigation. Networks like NASA's Deep Space Network, DSN, use radio signals to communicate with spacecraft, measuring the time it takes for a signal to travel to and from the craft. By analyzing these signals, engineers determine the spacecraft's distance, speed, and position. This method, known as two-way Doppler tracking, is highly accurate but becomes less effective as missions venture farther from Earth, where signal delays can span hours. Ground-based navigation also involves precise timing. Atomic clocks, accurate to within billionths of a second, ensure that signal measurements are reliable. These clocks are crucial for calculating distances and coordinating with spacecraft systems. As spacecraft travel to distant destinations like Mars or the outer planets, ground-based systems continue to serve as a vital lifeline, guiding them through critical maneuvers such as orbital insertions or landings. Onboard autonomy. As missions push deeper into space, the limitations of ground-based navigation become apparent. Communication delays, caused by the finite speed of light, prevent real-time decision-making for missions to Mars and beyond. For example, a command sent to a spacecraft near Mars can take up to 20 minutes to arrive and another 20 minutes for confirmation to return. This delay necessitates autonomous systems capable of making split-second decisions without human intervention. Modern spacecraft are equipped with sophisticated sensors, algorithms, and artificial intelligence to achieve autonomy. Star trackers, for instance, are optical devices that identify stars and use their positions to determine the spacecraft's orientation. Gyroscopes and accelerometers provide additional data on movement and velocity, allowing spacecraft to maintain precise trajectories. Autonomy is particularly critical during complex operations, such as landing on planetary surfaces or navigating around asteroids. The Mars rovers, for example, rely on autonomous systems to avoid hazards, choose paths, and even conduct scientific experiments. These systems use machine learning and real-time data analysis to adapt to changing conditions, ensuring mission success even in unpredictable environments. Navigating deep space. For interstellar missions, traditional navigation techniques face even greater challenges. The vast distances involved make it impractical to rely solely on ground-based systems. Instead, scientists are exploring novel methods of deep space navigation, such as using pulsars, rapidly spinning neutron stars that emit regular bursts of electromagnetic radiation. These cosmic beacons function like a natural GPS, providing fixed reference points for spacecraft to triangulate their position. Another emerging approach is optical navigation, which uses cameras to capture images of celestial objects, such as planets, moons, or stars. By comparing these images to onboard maps, a spacecraft can determine its position and adjust its trajectory. This method was used during NASA's New Horizons mission to Pluto, enabling precise navigation to a target billions of kilometers from Earth. The role of artificial intelligence. Artificial intelligence, AI, is revolutionizing spacecraft navigation and autonomy. AI systems can process vast amounts of data in real time, recognizing patterns and making decisions that would be impossible for human operators. For instance, AI algorithms can analyze images of asteroids or comets, identifying potential landing sites or hazards. AI also enables spacecraft to prioritize tasks, allocate resources, and even adapt to unexpected challenges, such as equipment malfunctions. Autonomy powered by AI is particularly important for long-duration missions. Probes sent to explore distant stars or galaxies must operate independently for decades, managing their systems, conserving energy, and conducting scientific experiments without human oversight. These capabilities will be essential for future missions, such as deploying robotic explorers to exoplanets or establishing permanent bases on Mars. Navigational challenges. Despite these advancements, spacecraft navigation is not without its difficulties. Gravitational perturbations from multiple celestial bodies can complicate trajectories, requiring continuous adjustments. Spacecraft must also contend with environmental factors like solar radiation, which can alter their paths over time. Engineers account for these influences by incorporating redundancy into systems and designing robust algorithms to handle uncertainties. Future innovations. Looking ahead, navigation technologies will continue to evolve. Quantum clocks, which promise even greater precision than current atomic clocks, could transform timing and positioning in space. Laser communication systems, capable of transmitting data with unprecedented speed and accuracy, will enhance spacecraft's ability to communicate their location. Additionally, advances in AI and machine learning will further empower spacecraft to operate autonomously, navigating the complexities of space with minimal human input. Spacecraft navigation and autonomy represent the convergence of physics, engineering, and computer science. They enable humanity to explore the cosmos with precision and resilience, turning the infinite void into a navigable realm. As missions venture deeper into the universe, the innovations in navigation will continue to guide us toward discoveries that redefine our understanding of existence. Fuel efficiency and refueling in space. Fuel is the lifeblood of space travel. Every maneuver, from launching into orbit to landing on distant worlds, depends on the availability and efficient use of fuel. Yet, the limitations of current propulsion technologies, combined with the sheer distances involved in space exploration, make carrying sufficient fuel a daunting challenge. How do we maximize fuel efficiency, and what innovations could enable refueling beyond Earth? At the core of this challenge is the Tsiolkovsky rocket equation, which reveals that a spacecraft's velocity is exponentially tied to its fuel-to-payload ratio. This relationship forces engineers to prioritize fuel efficiency at every stage of a mission, as carrying too much fuel significantly increases the spacecraft's mass, requiring even more fuel to propel it. This feedback loop, known as the tyranny of the rocket equation, drives the need for lighter spacecraft, efficient propulsion systems, and innovative refueling strategies. Maximizing fuel efficiency. Fuel efficiency in space travel depends on two primary factors: the propulsion system's specific impulse, a measure of fuel efficiency, and the spacecraft's trajectory. Traditional chemical rockets, though powerful, have a relatively low specific impulse, as they burn through propellants rapidly to generate thrust. To address this limitation, engineers have developed alternative propulsion technologies. 1. Ion propulsion. Ion thrusters, which use electric fields to accelerate ions, offer exceptional fuel efficiency. They consume minimal propellant while generating thrust over extended periods, allowing spacecraft to achieve high velocities with a fraction of the fuel required by chemical rockets. NASA's Dawn spacecraft, for example, used ion propulsion to visit the asteroid belt, demonstrating the technology's potential for long-duration missions. 2. Solar electric propulsion, SEP. SEP systems combine solar power with electric propulsion, using sunlight to generate electricity that powers ion thrusters. This approach extends fuel efficiency even further, as the spacecraft relies on solar energy rather than onboard fuel to sustain its operations. SCPE is being considered for missions to Mars and beyond, where prolonged journeys require minimal fuel consumption. 3. Nuclear thermal propulsion. By using a nuclear reactor to heat a propellant, nuclear thermal engines achieve higher exhaust velocities than chemical rockets, increasing specific impulse. This technology offers a balance between the high thrust of chemical rockets and the efficiency of electric propulsion, making it suitable for interplanetary missions. 4. Solar sails. Solar sails harness the momentum of photons from sunlight to propel a spacecraft. While the thrust is minimal, it requires no fuel, making it ideal for missions where time is less critical, but efficiency is paramount. The Japanese Icaro spacecraft successfully demonstrated this technology during its journey to Venus. In situ resource utilization, ISRU. Carrying all the required fuel for an interplanetary or interstellar mission is impractical. Instead, in situ resource utilization, ISRU, the process of extracting and using resources from space, offers a revolutionary solution. By refueling spacecraft using materials found on other celestial bodies, missions can reduce their initial fuel requirements and extend their range. 1. Lunar resources. The Moon is a prime candidate for ISRU, with abundant reserves of water ice in its polar regions. This ice can be mined and processed into hydrogen and oxygen, the components of rocket fuel. Establishing lunar fuel depots could transform the Moon into a refueling station for missions to Mars and beyond. 2. Martian atmosphere. Mars' thin atmosphere is rich in carbon dioxide, which can be converted into methane fuel using the Sabatier process. NASA's Perseverance rover is already testing this concept by producing oxygen from Mars CO2 using the MOXIE experiment, paving the way for future ISRU systems. 3. Asteroid mining. Asteroids contain water and other volatile compounds that can be converted into fuel. Mining these resources offers a sustainable way to refuel spacecraft during missions to the outer planets or even interstellar voyages. Robotic mining technologies and autonomous processing systems will play a crucial role in this endeavor. Orbital refueling stations. Building orbital refueling stations is another promising approach to extending mission durations and capabilities. These stations would store and distribute fuel, allowing spacecraft to refuel without returning to Earth. Concepts for such stations include: 1. Low Earth orbit LEO depots. Positioned in LEO, these depots could serve as initial refueling points for spacecraft heading to higher orbits or deep space. Fuel could be delivered to these depots via reusable rockets, minimizing costs. 2. Geostationary orbit and lunar orbit stations. Placing refueling depots in geostationary orbit or near the Moon would provide strategic points for interplanetary missions. These stations could store fuel produced via ISRU from the Moon, reducing dependency on Earth-based resupply. 3. Deep space refueling stations. Farther afield, refueling stations located near key gravitational landmarks, such as the Lagrange points, could support missions to the outer planets. These depots would require advanced technologies for fuel storage and transfer in microgravity. Challenges and innovations. While the concept of space-based refueling is compelling, it comes with significant technical and logistical challenges. Cryogenic fuel storage. Many rocket fuels, such as liquid hydrogen and liquid oxygen, require cryogenic storage at extremely low temperatures. Developing tanks and insulation that can maintain these temperatures in the harsh environment of space is essential. Fuel transfer in microgravity. Transferring fluids in microgravity presents unique challenges, as liquids behave differently without the influence of gravity. Engineers are developing systems that use capillary action and centrifugal force to ensure reliable fuel transfer. Energy requirements. Producing fuel in space requires energy-intensive processes, such as electrolysis to split water into hydrogen and oxygen. Advances in energy generation, such as nuclear reactors and high-efficiency solar panels, will be critical for powering these processes. The future of fuel in space. Fuel efficiency and refueling are pivotal to the future of space exploration. As humanity sets its sights on Mars, asteroids, and even the outer planets, these advancements will determine the feasibility and success of long-duration missions. ISRU and orbital refueling will enable spacecraft to travel farther, carry larger payloads, and conduct more ambitious scientific investigations. The concept of self-sustaining exploration, where spacecraft and colonies produce their own resources, represents the next evolutionary step in space travel. By mastering fuel efficiency and creating networks of refueling stations, humanity can transform the solar system into a navigable and accessible frontier, paving the way for our eventual journey to the stars. The speed of light, a barrier to interstellar travel? The speed of light, a universal constant at approximately 299,792 kilometers per second, about 186,282 miles per second, represents the ultimate speed limit of the universe as defined by Einstein's theory of relativity. While this cosmic speed limit is fundamental to our understanding of physics, it poses a monumental challenge to interstellar travel. Distances to even the nearest stars are measured in light years, making journeys at sublight speeds seem impossibly long. How do we grapple with this limitation, and are there ways to bypass or reimagine this boundary? The reality of interstellar distances. To appreciate the challenge, consider Proxima Centauri, the closest star to our solar system, located 4.24 light-years away. Traveling at the speed of light, it would take just over 4 years to reach it. However, with current technology, such as the New Horizons spacecraft that travels at around 58,000 kilometers per hour, 36,000 miles per hour, the journey would take over 70,000 years. This staggering timescale underscores the need for radically new approaches to propulsion and navigation. Why the speed of light is a limit. Einstein's special theory of relativity explains why nothing with mass can reach or exceed the speed of light. As an object accelerates toward the speed of light, its relativistic mass increases, requiring exponentially more energy to continue accelerating. At the speed of light, an object's mass would become infinite, and the energy required to propel it would also be infinite, making such acceleration impossible under current physical laws. This limitation also affects the passage of time. For a spacecraft traveling at relativistic speeds, close to the speed of light, time dilation would occur. Time would pass more slowly for the travelers compared to observers on Earth. While this phenomenon offers some advantages for the crew of an interstellar mission, allowing them to experience shorter perceived travel times, it does not reduce the journey's duration from the perspective of those left behind. Approaches to address the barrier. Despite the speed of light's apparent finality, scientists and engineers have proposed various strategies to approach or potentially surpass this limit. These concepts, ranging from advanced propulsion systems to speculative physics, push the boundaries of what is currently possible. 1. Achieving relativistic speeds. Advanced propulsion methods, such as nuclear fusion engines, antimatter propulsion, and light sails powered by lasers, could potentially accelerate spacecraft to a significant fraction of the speed of light. For instance, breakthrough Starshot envisions using ground-based lasers to propel ultralight spacecraft equipped with light sails to speeds of 20% the speed of light, enabling travel to Proxima Centauri in approximately 20 years. While this approach would not break the speed limit, it represents a practical way to achieve interstellar travel within a human lifetime. 2. Warp drives. Theoretical concepts like the Alcubierre warp drive propose bending spacetime itself to enable faster-than-light travel. This idea, rooted in general relativity, involves creating a warp bubble that contracts spacetime in front of the spacecraft and expands it behind, effectively moving the spacecraft faster than light relative to its surroundings. While intriguing, this concept requires exotic forms of energy, such as negative energy or matter, which have yet to be discovered or harnessed. 3. Wormholes. Wormholes, or Einstein-Rosen bridges, are theoretical shortcuts through spacetime that could connect distant regions of the universe. If traversable wormholes exist and could be stabilized, they might allow instantaneous travel across vast distances. However, the existence of wormholes remains speculative, and significant challenges, including their stability and the energy required to create them, must be addressed. 4. Time dilation and generational ships. Instead of attempting to surpass the speed of light, some proposals embrace the limitations and design missions around them. Relativistic time dilation could make interstellar travel feasible for the crew, as they would perceive shorter travel times even on journeys spanning decades or centuries. Alternatively, generational ships, self-sustaining spacecraft where multiple generations of humans live and die during the voyage, could accommodate the long timescales required to reach distant stars. 5. Quantum physics and the speed limit. Quantum mechanics introduces intriguing possibilities, such as quantum entanglement and tunneling, that seem to defy conventional notions of spacetime. While these phenomena have yet to be harnessed for practical space travel, they inspire ongoing research into the fundamental nature of the universe and its potential loopholes. Philosophical and practical implications. The speed of light as a barrier raises profound questions about humanity's place in the universe. If interstellar travel remains constrained by this limit, how do we reconcile our aspirations for exploration with the vastness of space? One possibility is to focus on sending robotic probes rather than human missions, leveraging advances in miniaturization, artificial intelligence, and long-term autonomy to explore distant systems. Alternatively, humanity might explore ways to expand its reach within the solar system, creating permanent settlements on planets, moons, and asteroids. By establishing a robust interplanetary civilization, we could lay the groundwork for eventual interstellar expansion. The future of interstellar exploration. While the speed of light imposes significant constraints, history has shown that human ingenuity often finds ways to overcome seemingly insurmountable challenges. Theoretical physics, emerging technologies, and innovative mission designs offer hope that interstellar travel might one day become a reality. Whether through the steady progress of relativistic propulsion, the discovery of exotic physics, or entirely new paradigms, humanity's drive to explore the cosmos will continue to push the boundaries of what is possible. The speed of light, rather than being a barrier, serves as a challenge, one that inspires us to reach for the stars. Cosmic radiation and shielding. The vastness of space may seem serene, but it is anything but peaceful. Invisible streams of high-energy particles, collectively known as cosmic radiation, constantly bombard the universe, posing a significant threat to both human and robotic explorers. Unlike Earth, which benefits from the protective shield of its magnetic field and atmosphere, space offers no such sanctuary. How can we protect astronauts and spacecraft from this relentless radiation, and what technologies are being developed to mitigate its effects? What is cosmic radiation? Cosmic radiation consists of energetic particles that originate from a variety of sources, including the sun, distant stars, and cataclysmic events like supernovae. It can be broadly categorized into three types. 1. Solar particle events, SPEs. These are bursts of charged particles, primarily protons, emitted by the sun during solar flares and coronal mass ejections. SPEs are relatively localized but can deliver intense radiation doses over short periods, posing acute risks to astronauts on spacewalks or unshielded spacecraft. 2. Galactic cosmic rays, GCRs. These high-energy particles come from outside our solar system, likely originating from supernova explosions and other energetic astrophysical events. GCRs consist of atomic nuclei stripped of electrons, including protons, helium nuclei, and heavier elements like iron. They are highly penetrating and pose long-term health risks. 3. Trapped radiation belts. In the vicinity of Earth, the Van Allen belts trap charged particles, creating localized zones of radiation. While spacecraft passing through these regions experience elevated exposure, their effects are temporary and can be mitigated with proper shielding. The risks of cosmic radiation. For astronauts, exposure to cosmic radiation can have severe biological effects. Short-term exposure to high doses, such as during a solar storm, can cause acute radiation sickness, with symptoms including nausea, fatigue, and damage to vital organs. Long-term exposure increases the risk of cancer, cardiovascular disease, and degenerative effects on the central nervous system. Radiation also damages spacecraft systems. High-energy particles can penetrate electronic components, causing single-event upsets, temporary glitches, latch-ups, circuit malfunctions, or even permanent damage. Optical systems, sensors, and solar panels are particularly vulnerable, as radiation can degrade materials over time. Shielding strategies. Effective shielding is essential for mitigating the risks of cosmic radiation. However, designing radiation shields is a complex trade-off between protection, weight, and cost. Several strategies are being explored. 1. Passive shielding. Traditional radiation shielding relies on physical barriers to absorb or deflect radiation. Common materials include aluminum. Widely used in spacecraft structures, aluminum provides basic protection against radiation, but is less effective against high-energy particles like GCRs. Polyethylene. Composed of lightweight hydrogen-rich molecules, polyethylene is highly effective at blocking radiation, especially protons. It is commonly used in spacecraft interiors and spacesuits. Water. Water is an excellent radiation shield and serves the dual purpose of providing life support. Some spacecraft designs incorporate water-filled walls to enhance protection. 2. Active shielding. Active shielding uses electromagnetic fields to deflect charged particles, mimicking the protective effects of Earth's magnetic field. Proposed systems include superconducting magnets, generating strong magnetic fields to repel charged particles. While promising, these systems require significant power and advanced cooling technologies. Electrostatic barriers, using charged surfaces to create electric fields that deflect particles. This approach is still in its experimental phase. 3. Biological countermeasures. Advances in biology and medicine offer additional ways to mitigate radiation risks. Pharmaceuticals, drugs that protect DNA or repair damage caused by radiation, are under development. For example, antioxidants and radioprotective compounds may reduce cellular damage. Genetic engineering. Research into modifying human cells to enhance natural radiation resistance is a speculative but intriguing area of study. 4. Innovative materials. Cutting-edge materials are being developed to improve radiation shielding. Hydrogenated boron nitride nanotubes, HBNNTs, lightweight, hydrogen-rich materials that offer superior radiation protection while maintaining structural integrity. Regolith-based shields, utilizing local materials such as lunar or Martian soil to build protective habitats. This approach reduces the need to transport shielding materials from Earth. Applications for spacecraft and habitats. Radiation shielding is tailored to the specific needs of missions. For example, crewed spacecraft. Vehicles like SpaceX's Starship and NASA's Orion are designed with radiation-safe zones, where astronauts can shelter during solar storms. Space stations. The International Space Station, ISS, uses polyethylene and water tanks as shielding. Future stations, like those planned for lunar orbit, will require enhanced protection against cosmic radiation. Lunar and Martian habitats. Permanent settlements will likely be built underground or covered with thick layers of regolith to shield inhabitants from GCRs and solar radiation. Monitoring and early warning systems. Real-time monitoring of radiation levels is crucial for astronaut safety. Instruments like dosimeters track cumulative radiation exposure, while space weather forecasting systems predict solar storms and other events. Advanced sensors aboard spacecraft and satellites help provide early warnings, allowing crews to take shelter or delay extravehicular activities during high radiation events. Challenges and future innovations. Despite significant progress, radiation shielding remains one of the most challenging aspects of space exploration. Key obstacles include weight constraints. Effective shielding materials are often heavy, increasing launch costs and limiting payload capacity. Cost of development. Advanced materials and active shielding technologies require substantial investment and testing. Unknowns in deep space. The radiation environment beyond the solar system is poorly understood, adding uncertainty to interstellar mission planning. Future innovations could address these challenges, including self-healing materials. Materials capable of repairing radiation-induced damage autonomously could extend the lifespan of spacecraft. Artificial magnetic fields. Compact and energy-efficient systems for generating magnetic or electrostatic fields could revolutionize active shielding. Integrated shielding. Combining life support systems, structural components, and radiation protection into multifunctional designs could optimize spacecraft interiors. The path forward. As humanity prepares for missions to Mars, the Moon, and beyond, radiation shielding will be a cornerstone of spacecraft and habitat design. Addressing the cosmic radiation challenge not only ensures the safety of astronauts, but also advances technologies that could benefit Earth-based industries, from healthcare to materials science. Surviving the cosmic bombardment of space is a testament to our ingenuity and determination. Each solution we develop brings us closer to realizing our dreams of exploring the stars, turning the hostile expanse of space into a realm of opportunity and discovery. The concept of artificial gravity. In the microgravity of space, the absence of a constant downward force has profound effects on both humans and equipment. Astronauts experience muscle atrophy, bone density loss, and changes to cardiovascular and neurological systems, while fluids redistribute in the body, causing disorientation and other health issues. Long-duration missions, such as journeys to Mars or permanent habitation on other planets, magnify these challenges, making artificial gravity a critical consideration. But how can we simulate gravity in the weightless void of space? What technologies and physics principles can recreate this essential force? The physics behind artificial gravity. Gravity, as we experience it on Earth, is a force of attraction between two masses, dictated by Newton's law of gravitation. In the absence of such a force, artificial gravity can be simulated through centripetal force, which mimics gravitational pull by spinning an object. When a spacecraft or part of it rotates, objects and occupants inside experience an outward force, known as centrifugal force, directed away from the axis of rotation. This force can replicate the effects of gravity, depending on the rotation speed and the radius of the rotating structure. The artificial gravity, GGG generated by rotation, is calculated using the formula G equals omega to RG equals backslash omega caret 2 RG equals omega to R, where omega backslash omega is the angular velocity, rate of spin. RRR is the radius of the rotating structure. This formula highlights the trade-offs involved in designing artificial gravity systems. A larger radius requires slower rotation to achieve the same gravitational effect, reducing the risk of dizziness and discomfort. Conversely, smaller structures must spin faster, which can cause adverse effects due to Coriolis forces. Implementations of artificial gravity. Several designs and concepts for generating artificial gravity have been proposed and tested, ranging from small-scale systems for current missions to large habitats envisioned for the future. 1. Rotating spacecraft. One of the simplest designs involves spinning an entire spacecraft to create artificial gravity throughout its interior. This concept, popularized by science fiction films like 2001: A Space Odyssey, offers a unified environment where occupants can move and work under consistent gravity. However, spinning large spacecraft presents significant engineering challenges, including structural stresses and maintaining stability during propulsion. 2. Tethered systems. A more practical approach for current technology is a two-part spacecraft connected by a long tether. By spinning the system around a central axis, centripetal force generates artificial gravity at the ends. This configuration allows for adjustable gravity levels by varying the tether length and spin rate. Tethered systems are relatively lightweight and modular, but require precise control to avoid tangling or destabilization. 3. Rotating habitats. For permanent settlements, such as lunar or Martian bases, rotating habitats provide a scalable solution. These structures could range from small rotating rooms to large wheels or toruses. The Stanford Torus, a conceptual design for a space habitat, features a massive rotating ring where centrifugal force creates Earth-like gravity for its inhabitants. Such designs promise long-term habitability, but require extensive materials and energy to construct. 4. Centrifuges inside spacecraft. For missions that don't spin the entire spacecraft, centrifuges can provide localized artificial gravity. These spinning chambers or platforms allow astronauts to spend part of their day in a gravity-like environment, reducing the health impacts of prolonged weightlessness. NASA has tested small centrifuge prototypes, but integrating them into spacecraft interiors remains a design challenge. Challenges and limitations. While artificial gravity offers numerous benefits, its implementation is far from straightforward. Key challenges include: 1. Structural integrity. The stresses induced by rotation, especially in large systems, require materials that can withstand significant forces without adding excessive weight. Advanced composites and lightweight alloys are critical for constructing durable, efficient structures. 2. Energy requirements. Maintaining rotation, particularly in tethered or large-scale systems, consumes energy. Engineers must balance the energy demands of artificial gravity with other spacecraft systems, such as propulsion and life support. 3. Coriolis effects. Rapid rotation in small systems can cause Coriolis forces, which affect the movement of objects and fluids. Astronauts in such environments may experience disorientation, nausea, or difficulty performing tasks. To minimize these effects, systems must either rotate slowly, necessitating larger structures, or acclimatize occupants to the forces over time. 4. Design integration. Incorporating artificial gravity into spacecraft or habitats involves trade-offs with other design priorities, such as maximizing usable space, ensuring stability, and protecting against radiation. Modular designs and adaptive systems can help address these constraints. Benefits for human health. The most compelling argument for artificial gravity is its potential to mitigate the physiological challenges of microgravity. Studies on the International Space Station, ISS, have shown that astronauts lose approximately 1% of their bone density per month in microgravity, despite rigorous exercise routines. Muscle atrophy, cardiovascular deconditioning, and vision impairment are additional concerns. Artificial gravity could preserve bone and muscle strength by providing a constant load on the body, normalize fluid distribution, reducing pressure on the head and eyes, support cardiovascular function by maintaining consistent blood flow patterns. Future applications. Artificial gravity is likely to play a central role in long-duration missions and permanent settlements. Some potential applications include Mars missions. Crewed missions to Mars, which may last several years, could incorporate tethered systems or centrifuge modules to reduce health risks during transit. Lunar bases. Rotating habitats on the Moon could supplement the Moon's weak gravitational field, which is only 16.5% as strong as Earth's. Space stations. Next-generation space stations may integrate artificial gravity to enable longer stays and more ambitious scientific research. Current research and prototypes. Research into artificial gravity is gaining momentum. Space agencies like NASA, ESA, and private organizations are exploring centrifuge designs, rotating modules, and other technologies. Notable projects include NASA's Centrifuge Module, a prototype for creating partial gravity environments aboard the ISS, which provides insights into how artificial gravity affects the human body. MIT's toroidal habitats, concepts for lightweight, modular toroidal habitats designed to provide artificial gravity in orbit. The path forward. While artificial gravity remains largely conceptual, its development is essential for humanity's expansion into space. By addressing the physiological challenges of microgravity, artificial gravity will enable longer, healthier missions, paving the way for sustainable exploration of the Moon, Mars, and beyond. As engineers and scientists refine designs, the dream of living and working comfortably in space becomes increasingly attainable. Artificial gravity is not merely a tool for survival. It is a step toward creating permanent human outposts in the cosmos, transforming the hostile void of space into a second home. Navigating wormholes and warp drives. The vast distances between stars present an almost insurmountable challenge for traditional space travel methods. Even with advanced propulsion systems capable of approaching a significant fraction of the speed of light, interstellar journeys would take decades, centuries, or longer. This limitation has led scientists and futurists to explore more exotic concepts: wormholes and warp drives. These theoretical phenomena, grounded in the physics of space-time, offer tantalizing possibilities for faster-than-light (FTL) travel. But how realistic are these ideas? And what hurdles must we overcome to turn them from science fiction into science fact? Wormholes, shortcuts through space-time. Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures that connect two distant points in space-time. Imagine folding a piece of paper so that 2 points touch. A wormhole, in theory, provides a tunnel through this fold, allowing near-instantaneous travel between the points. The concept of wormholes arises from Einstein's general theory of relativity, which describes how massive objects distort space-time. Mathematically, certain solutions to Einstein's field equations suggest the possibility of wormholes. These structures could potentially link distant regions of space, time, or even parallel universes. Types of wormholes. 1. Traversable wormholes. A traversable wormhole would allow matter to pass through without being destroyed. Theoretical physicist Kip Thorne and his colleagues explored the conditions under which such wormholes might exist, concluding that exotic matter with negative energy density would be required to keep the wormhole stable and open. This exotic matter, while theoretically possible, has not been observed. 2. Non-traversable wormholes. Most naturally occurring wormholes, if they exist, are thought to be non-traversable. They collapse too quickly for anything to pass through, acting more like cosmic curiosities than practical travel corridors. Challenges of wormholes. Exotic matter. To stabilize a wormhole, exotic matter with negative energy is required. While quantum effects, such as the Casimir effect, suggest that negative energy might exist, producing or harnessing it on a large scale remains purely theoretical. Instability. Even with exotic matter, maintaining a stable wormhole would be immensely challenging. Gravitational fluctuations, cosmic radiation, or even the passage of a single particle could cause the structure to collapse. Causality issues. Wormholes could allow for time travel, leading to paradoxes that challenge our understanding of physics. These causality violations raise questions about the fundamental consistency of wormhole-based travel. Despite these obstacles, the study of wormholes continues to inspire both scientific inquiry and speculative fiction. If such structures could be created or discovered, they would revolutionize space travel, making interstellar journeys instantaneous. Warp drives, manipulating space-time. The concept of warp drives, popularized by science fiction like Star Trek, involves bending space-time itself to achieve FTL travel. Unlike wormholes, which act as shortcuts, a warp drive compresses space-time in front of a spacecraft and expands it behind. This creates a bubble in which the spacecraft can effectively ride through space-time without violating the speed of light within its local frame. The Alcubierre drive. In 1994, physicist Miguel Alcubierre proposed a theoretical framework for a warp drive based on Einstein's equations. The Alcubierre drive would create a warp bubble around a spacecraft, allowing it to travel faster than light relative to an external observer. Inside the bubble, space-time remains flat, preserving the laws of physics. Challenges of warp drives. 1. Exotic energy requirements. Like wormholes, warp drives require exotic matter or negative energy to manipulate space-time. Early calculations suggested that the energy needed to power an Alcubierre drive would exceed the mass energy of the observable universe. Later refinements reduced this requirement, but still placed it far beyond current technological capabilities. 2. Energy distribution. The creation and control of a warp bubble would require precise manipulation of energy fields, which poses immense engineering challenges. 3. Radiation hazards. As a warp bubble moves through space-time, it could accumulate high-energy particles. When the bubble is deactivated, these particles might be released in a catastrophic burst of radiation. 4. Stability and directionality. Ensuring that a warp bubble remains stable and can be directed toward a specific destination is another unresolved issue. Recent developments. Recent research has explored ways to make warp drives more feasible. In 2021, physicist Eric Lentz proposed a theoretical model for a warp drive that does not rely on negative energy, instead using configurations of conventional matter. While still highly speculative, this represents a step toward reconciling warp drive concepts with known physics, quantum physics, and exotic possibilities. Beyond general relativity, quantum mechanics offers additional possibilities for FTL travel. Concepts such as quantum entanglement and quantum tunneling hint at phenomena that could bypass the limitations of classical spacetime. While these ideas are far from practical application, they challenge our understanding of causality and locality, opening new avenues for exploration. Philosophical and practical implications. Wormholes and warp drives, if achievable, would not only revolutionize space travel, but also fundamentally alter our understanding of the universe. Instantaneous travel would enable unprecedented exploration, interstellar commerce, and communication. However, it would also raise profound ethical and existential questions. Causality and free will. If wormholes or warp drives allow for time travel, how do we reconcile this with our sense of cause and effect? Access and power. Who controls such technologies, and how are they regulated? The implications for geopolitics and interstellar relations are staggering. Human identity. What does it mean to journey across light years in an instant? How would such capabilities reshape our understanding of distance, isolation, and connection? The path forward. While wormholes and warp drives remain speculative, their study pushes the boundaries of physics, inspiring new questions and insights. Advances in quantum mechanics, cosmology, and material science could one day bring us closer to turning these theoretical constructs into reality. For now, they serve as powerful reminders of humanity's boundless curiosity and determination to explore the unknown. Whether through incremental advancements or paradigm-shifting discoveries, the dream of transcending the speed of light continues to drive our quest for the stars. Communication across the vastness of space. In the boundless expanse of space, where even light takes years to traverse between stars, communication poses one of the most daunting challenges. Whether sending instructions to robotic explorers, coordinating missions with crewed spacecraft, or receiving data from interstellar probes, the vast distances and inherent delays demand innovative solutions. How do we communicate effectively across the cosmos? And what technologies are emerging to bridge the unimaginable gaps? The basics of space communication. Spacecraft communication relies on electromagnetic waves, such as radio waves, microwaves, and laser beams, to transmit information. These signals travel at the speed of light, allowing relatively fast communication within the Earth-Moon system, but creating significant delays for interplanetary and interstellar distances. For instance, a signal sent to Mars at its closest approach takes approximately 4 to 24 minutes for a round trip, depending on the relative positions of Earth and Mars. A message to Voyager 1, the farthest human-made object, takes over 21 hours one way due to its distance of over 23 billion kilometers from Earth. The delays grow exponentially as missions venture farther, making real-time communication impossible for interstellar exploration. Challenges in deep space communication. 1. Signal strength and attenuation. As signals travel vast distances, they weaken due to spreading and interference. This attenuation reduces the strength and clarity of the message, requiring powerful transmitters, sensitive receivers, and sophisticated error correction protocols to ensure data integrity. 2. Latency. Communication delays limit the ability to control spacecraft in real time, requiring missions to incorporate autonomy and pre-programmed instructions. For crewed missions, delayed responses from Earth could complicate emergency situations. 3. Bandwidth limitations. The farther a spacecraft travels, the harder it becomes to maintain high data transmission rates. Interstellar probes would face severe bandwidth constraints, limiting the volume of scientific data they can send back. 4. Alignment and signal loss. Spacecraft and ground stations must maintain precise alignment to ensure signals are transmitted and received accurately. Even small deviations can lead to signal loss, particularly when communicating with fast-moving or distant objects. Current communication technologies. 1. Radio waves. Traditional space communication relies on radio frequencies, which are reliable and well understood. NASA's Deep Space Network, DSN, a global system of radio antennas, is the backbone of communication for deep space missions. The DSN's large dish antennas, up to 70 meters in diameter, amplify weak signals from distant spacecraft. 2. Microwaves. Microwaves, a subset of radio waves, offer higher frequencies and greater data carrying capacity. They are commonly used for interplanetary missions, including Mars rovers and orbiters. 3. Lasers and optical communication. Laser communication, or optical communication, is an emerging technology that offers significantly higher data rates compared to radio waves. By using tightly focused laser beams, spacecraft can transmit vast amounts of data with minimal signal loss. NASA's Laser Communications Relay Demonstration, LCRD, and the European Space Agency's, ESA, laser-based systems are paving the way for optical communication in future missions. Innovations for interstellar communication. 1. High-energy lasers. For interstellar probes, lasers powered by onboard nuclear energy or large-scale solar arrays could provide a reliable means of transmitting data back to Earth. The precision of lasers reduces signal dispersion, making them ideal for spanning light years. 2. Quantum communication. Quantum entanglement, a phenomenon where particles remain interconnected regardless of distance, offers the potential for instantaneous communication. While this remains theoretical, experiments in quantum teleportation and entangled photon pairs suggest it could one day revolutionize interstellar communication. 3. Relays and networks. Deploying relay stations at key points, such as in orbit around planets or at Lagrange points, could facilitate more efficient communication. These stations would serve as intermediaries, boosting signals and reducing direct alignment requirements between spacecraft and Earth. 4. Autonomous systems. As delays make real-time control impossible, spacecraft must operate autonomously, analyzing data, making decisions, and prioritizing transmissions. Artificial intelligence, AI, and machine learning are critical for enabling this level of autonomy. The role of artificial intelligence. AI plays a pivotal role in managing the complexities of space communication. From optimizing signal paths to compressing data for efficient transmission, AI systems enhance the reliability and effectiveness of communication networks. In interstellar missions, AI could prioritize critical data, detect and correct errors, and adapt communication strategies based on evolving conditions. Preparing for interstellar communication. Future interstellar missions, such as Breakthrough Starshot's plan to send light sail probes to Alpha Centauri, require entirely new communication paradigms. These probes, traveling at 20% the speed of light, would face extraordinary challenges in transmitting data over 4.24 light-years. Proposed solutions include ultra-precise laser arrays capable of maintaining alignment across vast distances, advanced error correction algorithms to preserve data integrity despite weak signals, compact, high-efficiency transmitters and receivers designed to operate in extreme environments. The challenges of delay and isolation. While faster data transmission technologies address some technical issues, the fundamental limitation of light-speed communication imposes psychological and logistical challenges. For crewed missions to Mars or beyond, delayed responses from Earth necessitate greater independence and resilience among astronauts. Effective pre-mission training, onboard AI assistance, and robust decision-making protocols are essential to mitigate these challenges. The future of interstellar messaging. As humanity ventures deeper into space, the way we communicate will evolve. Interstellar probes. Communication technologies must prioritize compactness, energy efficiency, and reliability. Exoplanetary exploration. Advanced arrays and networks will enable data transmission from probes exploring planets and other star systems. Human expansion. For future space colonies, Networks of orbiting satellites and relays will create local intranets, reducing dependence on Earth-based systems. Philosophical implications. Communication across cosmic distances raises profound questions about humanity's place in the universe. If we detect intelligent extraterrestrial signals, how would we respond given the immense time delays? What role does communication play in defining human connection when physical and temporal separation grows beyond comprehension? The path ahead. Advancements in communication technologies are vital to the success of future missions. Whether developing quantum systems, refining laser communication, or enhancing AI-driven autonomy, humanity's ability to stay connected across the vastness of space will determine the scope of our exploration and the stories we bring back from the stars. Energy sources for space travel. Energy is the lifeblood of space travel, powering propulsion systems, life support, communication, and scientific instruments. As missions venture farther from Earth and grow more complex, finding reliable and sustainable energy sources becomes paramount. What technologies power today's spacecraft, and what innovations are shaping the future of energy in space? Energy challenges in space. The hostile environment of space presents unique challenges for energy generation and storage. Distance from the sun. Solar energy becomes less effective as missions move farther from the sun. For example, at Jupiter, sunlight is only 4% as intense as it is near Earth, requiring larger solar arrays. Weight constraints. Launch costs and payload limitations demand lightweight and efficient energy systems. Continuous operation. Energy systems must operate reliably in environments ranging from the intense radiation near the sun to the extreme cold of deep space. Long-duration missions. Missions to the outer planets or interstellar space require energy solutions that last decades or even centuries. Current energy systems. 1. Solar power. Solar power is the most common energy source for spacecraft operating within the inner solar system. Solar panels convert sunlight into electricity, providing a clean and renewable energy supply. Advances in photovoltaic technology have made solar panels lighter, more efficient, and more durable. Applications. Solar panels are used on satellites, Mars rovers like Perseverance, and space stations like the International Space Station, ISS. Limitations. Solar power diminishes with distance from the sun and can be disrupted by planetary shadows or dust storms, such as those on Mars. 2. Chemical batteries. Batteries store energy for short-term use, particularly during periods when solar panels cannot generate power, such as during planetary eclipses or on the night side of celestial bodies. Applications. Lithium-ion batteries are commonly used in conjunction with solar power, as seen on the Mars rovers. Limitations. Batteries have limited capacity and require regular recharging, making them unsuitable for long-duration missions. 3. Radioisotope thermoelectric generators, RTGs. RTGs convert heat from the radioactive decay of isotopes like plutonium-238 into electricity. They are highly reliable and can operate for decades without sunlight, making them ideal for deep space missions. Applications. RTGs power spacecraft such as Voyager, Cassini, and the Mars Curiosity rover. Limitations. The availability of suitable isotopes is limited, and their use raises concerns about safety and environmental impact. 4. Fuel cells. Fuel cells generate electricity through chemical reactions, typically involving hydrogen and oxygen. They offer high energy density and are used for short-term, high-power applications. Applications. The Apollo missions relied on fuel cells for energy. Limitations. Fuel cells are heavy and consume finite resources, limiting their duration of use. Emerging energy technologies. As missions grow more ambitious, new energy systems are being developed to overcome the limitations of current technologies. 1. Nuclear fission reactors. Small modular nuclear reactors, capable of generating kilowatts to megawatts of power, are being designed for use in space. Fission reactors provide a steady and abundant energy supply, making them suitable for lunar bases, Mars habitats, and deep space exploration. Projects. NASA's Kilo Power project demonstrated a prototype reactor capable of producing up to 10 kilowatts of electricity. Advantages. Unlike solar power, Fission reactors are unaffected by distance from the sun or environmental conditions. Challenges: developing lightweight, safe, and compact reactors for space use remains a technical hurdle. 2. Fusion energy. Nuclear fusion, the process that powers the sun, offers the promise of nearly limitless energy. Fusion reactors would use isotopes like deuterium and helium-3 to produce energy through the fusion of atomic nuclei. Potential applications: fusion propulsion systems could provide both energy and thrust for interstellar missions. Challenges: containing and sustaining fusion reactions in space is a major technological barrier. 3. Advanced solar technologies. Innovations in solar energy aim to extend its viability for deeper space missions. Concentrated solar power, CSP, uses mirrors or lenses to focus sunlight onto small, high-efficiency solar cells, increasing energy output. Thin-film solar cells. Lightweight and flexible, these cells can cover larger areas with less mass. Solar sails. Instead of converting sunlight into electricity, solar sails use the momentum of photons to propel spacecraft, offering a fuel-free propulsion method. 4. Beamed energy systems. Beamed energy involves transmitting energy to spacecraft using lasers or microwaves. This approach allows spacecraft to operate without carrying heavy energy sources on board. Applications: beamed energy could power light sail spacecraft or recharge lunar bases from orbiting satellites. Challenges: maintaining precise alignment over vast distances and ensuring efficient energy transfer are significant obstacles. 5. Dynamic energy harvesting. Spacecraft can harvest energy from environmental sources, such as motion, temperature gradients, or magnetic fields. For example, thermal energy harvesting converts heat differentials into electricity. Vibration energy harvesting generates power from mechanical vibrations or oscillations. Energy storage innovations. Efficient energy storage is critical for ensuring consistent power supply, especially during periods when energy generation is not possible. Emerging storage technologies include solid-state batteries, offering higher energy density and safety compared to traditional lithium-ion batteries. Supercapacitors, providing rapid charge and discharge cycles for short-term energy needs. Cryogenic energy storage, storing energy as liquid hydrogen or oxygen, which can also serve as rocket propellant. Applications for long-duration missions. 1. Lunar and Martian bases. Sustainable energy systems are essential for off-world colonies. Solar panels combined with energy storage systems are suitable for the Moon, while nuclear reactors are likely the best option for Mars, where dust storms can block sunlight for weeks. 2. Outer planet exploration. Missions to Jupiter, Saturn, and beyond require energy systems that can operate reliably far from the sun. RTGs and nuclear reactors are the leading candidates for powering scientific instruments and propulsion systems. 3. Interstellar probes. For missions to other star systems, energy systems must last decades or centuries. Fusion reactors, beamed energy, or advanced nuclear technologies are the most promising solutions. 4. Space mining and industry. Extracting resources from asteroids or other celestial bodies requires robust and scalable energy systems. Solar power, supplemented by in-situ energy generation, could enable large-scale mining operations. The future of space energy. Energy systems are the cornerstone of humanity's expansion into the cosmos. As we push the boundaries of exploration, the development of efficient, reliable, and sustainable energy technologies will determine the success of missions. From powering deep space probes to enabling permanent settlements on other worlds, energy innovations will transform the vision of space travel into a lasting reality. The role of robotics and AI in space travel. As space exploration grows more ambitious, the role of robotics and artificial intelligence, AI, becomes increasingly vital. From performing high-risk tasks to enabling autonomous decision-making, robots and AI systems are essential for missions that push the limits of human capabilities. How are these technologies transforming space travel? And what does the future hold for their integration into exploration, research, and settlement? Why robotics and AI are essential. Space exploration involves environments that are inherently hostile to humans. Extreme temperatures, radiation, microgravity, and vast distances make many tasks impractical or dangerous for human astronauts. Robots and AI address these challenges by enhancing safety. Robots can operate in conditions too hazardous for humans, such as the surface of Venus or the depths of lunar craters. Increasing efficiency. Automated systems perform repetitive or complex tasks more quickly and accurately than humans. Reducing costs. Robots and AI reduce the need for large, life-supporting spacecraft, lowering mission costs. Enabling autonomy. For missions where real-time communication with Earth is impossible due to light-speed delays, AI systems make critical decisions independently. Current applications of robotics in space. 1. Exploration rovers. Robotic rovers are a cornerstone of planetary exploration. Equipped with cameras, sensors, and scientific instruments, they analyze terrain, gather samples, and conduct experiments. Examples. NASA's Perseverance rover is exploring Mars, searching for signs of ancient life and collecting samples for eventual return to Earth. China's Yutu-2 rover operates on the far side of the Moon, studying geology and radiation levels. 2. Spacecraft maintenance. Robotic arms, such as those on the International Space Station, ISS, perform maintenance tasks, including repairing equipment, installing instruments, and capturing resupply vehicles. Examples. Canada's Canadarm2 is a versatile robotic arm used for ISS operations. The European Robotic Arm, ERA, assists with assembly and maintenance on the Russian segment of the ISS. 3. Satellite servicing. Robots are being developed to repair, refuel, or upgrade satellites, extending their operational lifespans and reducing space debris. Examples. NASA's Restore-L mission aims to demonstrate autonomous satellite servicing. DARPA's Robotic Servicing of Geosynchronous Satellites, RSGS, program focuses on military and commercial satellite maintenance. 4. Sample return missions. Robotic systems are critical for missions that collect samples from other celestial bodies and return them to Earth. Examples. Japan's Hayabusa 2 successfully retrieved samples from the asteroid Ryugu. NASA's OSIRIS-RX returned material from the asteroid Bennu. 5. Autonomous landing and navigation. Robots equipped with AI can land on challenging terrain with minimal human input. For example, the Perseverance rover used terrain-relative navigation to land safely on Mars. The role of AI in space travel. AI complements robotics by enabling intelligent decision-making and adaptability in unpredictable environments. Key applications of AI include 1. Autonomous navigation. AI algorithms allow spacecraft and rovers to navigate without human intervention. By analyzing sensor data, these systems avoid obstacles, optimize paths, and adjust to changing conditions. Examples. The Mars rovers use AI to autonomously traverse rocky terrain. The ESA's Bepi-Colombo mission to Mercury relies on AI to manage its complex trajectory. 2. Data analysis and scientific discovery. AI processes vast amounts of data generated by spacecraft, identifying patterns and anomalies that might be missed by human analysts. Examples. AI systems on telescopes and satellites identify exoplanets by analyzing light curves. NASA's Frontier Development Lab uses AI to study solar activity and predict space weather. 3. Human-robot collaboration. AI enables seamless interaction between astronauts and robotic systems. Robots equipped with natural language processing and machine learning assist with tasks ranging from equipment repairs to scientific experiments. Examples. The Simon Crew Interactive Mobile Companion system aboard the ISS uses AI to assist astronauts with research tasks. Robonaut, a humanoid robot, performs maintenance tasks on the ISS. 4. Autonomous problem solving. AI systems diagnose and address issues on board spacecraft without waiting for instructions from Earth, ensuring mission continuity. Examples. AI algorithms on satellites detect and mitigate hardware failures. The European Space Operations Center, ESOC, uses AI to manage spacecraft anomalies. Advanced robotics for future missions. As humanity prepares for more complex missions, next-generation robots are being developed to tackle unprecedented challenges. 1. Lunar and Martian construction. Robots will play a key role in building habitats, extracting resources, and setting up infrastructure for human settlements. Examples: NASA's RASER, Regolith Advanced Surface Systems Operations Robot, is designed for excavating lunar and Martian soil. Autonomous 3D printing robots could construct habitats using local materials. 2. Interstellar exploration. Tiny robotic probes equipped with AI are the most feasible way to explore distant star systems. Projects like Breakthrough Starshot aim to send light sail-powered probes to Alpha Centauri. Advantages: these probes can operate autonomously for decades, transmitting data back to Earth without human intervention. 3. Bio-inspired robotics. Robots modeled after living organisms, such as insects or snakes, offer enhanced mobility and adaptability. These designs are ideal for exploring complex terrain, such as caves or lava tubes on Mars. Examples: NASA's Braille project, biologic and resource analog investigations in low-light environments, explores bio-inspired designs for subterranean exploration. The role of AI in long-duration missions. For crewed missions to Mars or beyond, AI will be indispensable in managing life support systems, conducting scientific research, and supporting crew well-being. Examples include medical assistance. AI systems can monitor astronauts' health, diagnose conditions, and provide treatment recommendations. Resource management. AI optimizes the use of water, oxygen, and energy, ensuring sustainability during long missions. Psychological support. AI companions can provide social interaction and emotional support, mitigating the isolation of deep space travel. Ethical and safety considerations. As robotics and AI become more integrated into space travel, ethical and safety concerns must be addressed. Autonomy versus control. How much autonomy should robots and AI have in critical decision-making? Accountability. Who is responsible for failures or unintended consequences caused by autonomous systems? Bias and fairness. Ensuring AI systems operate fairly and without bias in diverse and unpredictable environments. The path forward. Robotics and AI are transforming the way humanity explores space, enabling missions that were once thought impossible. As these technologies advance, they will not only expand the reach of exploration, but also pave the way for sustainable human presence beyond Earth. From autonomous rovers on distant planets to intelligent assistants aboard spacecraft, the synergy between robotics and AI represents the next frontier in space travel, bridging the gap between ambition and capability. Terraforming and physics. Terraforming, the process of transforming a planet or moon into a habitable environment resembling Earth, is one of the most ambitious and speculative concepts in space exploration. With humanity's growing interest in colonizing worlds like Mars, the Moon, or even Venus, understanding the physics of terraforming is crucial. What would it take to create a breathable atmosphere, liquid water, and sustainable ecosystems on alien worlds? And how realistic are these visions? The challenges of terraforming. Terraforming a celestial body involves altering its fundamental environmental conditions, including atmosphere, creating a breathable atmosphere with the right pressure and composition. Temperature, adjusting the surface temperature to allow for liquid water and Earth-like climates. Radiation protection, shielding inhabitants from harmful cosmic and solar radiation. Magnetic field, generating a protective magnetic field to prevent atmospheric loss. Each of these challenges requires the application of advanced physics, engineering, and planetary science. Terraforming Mars, a case study. Mars is the most likely candidate for terraforming due to its proximity to Earth, abundant water ice, and evidence of a once thicker atmosphere. However, it presents significant obstacles. Thin atmosphere. Mars' atmosphere is 100 times thinner than Earth's, composed primarily of carbon dioxide, CO2. Cold temperatures. The average surface temperature is about -60 degrees Celsius, -80 degrees Fahrenheit, with extreme variability. Radiation exposure. Without a magnetic field, Mars is exposed to high levels of cosmic and solar radiation. Strategies for terraforming Mars. 1. Thickening the atmosphere. A thicker atmosphere would trap heat and increase surface pressure, enabling liquid water to exist. Proposed methods include releasing greenhouse gases, CO2 trapped in polar ice caps and Martian regolith could be released by heating the planet using giant mirrors or nuclear-powered stations. Importing volatiles. Asteroids rich in ammonia or other greenhouse gases could be redirected to impact Mars, releasing gases upon impact. Industrial emissions. Factories on Mars could produce greenhouse gases like perfluorocarbons, PFCs, which are potent heat-trapping molecules. 2. Raising surface temperatures. Increasing the temperature involves trapping more heat through greenhouse effects or direct heating. Solar reflectors. Placing large mirrors in orbit around Mars could reflect additional sunlight onto the surface. Nuclear reactors. Reactors could generate heat locally, melting ice and releasing gases. Dust storms. Artificially creating dust storms might increase surface warming by trapping heat in the atmosphere. 3. Creating liquid water sources. Liquid water is essential for life as we know it. Strategies include melting polar ice caps. Heating the ice caps could release water and CO2. Subsurface exploration. Tapping into underground reservoirs of water or brine. 4. Generating oxygen. To make the atmosphere breathable, oxygen levels would need to increase significantly. Proposed methods include photosynthetic organisms. Introducing genetically engineered microbes or plants to produce oxygen through photosynthesis. Electrolysis of water. Using solar or nuclear power to split water molecules into hydrogen and oxygen. 5. Building radiation shields. Without a magnetic field, terraform Mars would still be vulnerable to radiation. Solutions include atmospheric shielding. A thicker atmosphere would provide some protection by absorbing radiation. Artificial magnetic field. A magnetic field could be generated using large superconducting magnets at strategic locations, such as Mars Lagrange points. Underground habitats. Building initial settlements below the surface would protect colonists from radiation. Terraforming Venus. A different challenge. Venus, with its thick, toxic atmosphere and extreme temperatures, presents a vastly different set of challenges. Atmosphere. Venus' atmosphere is 90 times denser than Earth's, composed mostly of CO2 and clouds of sulfuric acid. Temperature. Surface temperatures exceed 450 degrees Celsius 842 degrees Fahrenheit, hot enough to melt lead. Slow rotation. A day on Venus lasts 243 Earth days, complicating heat distribution. Strategies for terraforming Venus. 1. Reducing atmospheric pressure. Venus' atmosphere would need to be drastically thinned to reduce pressure and temperature. This could involve removing CO2, using massive orbital mirrors to reflect sunlight, cooling the planet and condensing CO2 in a solid or liquid form, exporting atmosphere, redirecting portions of Venus' atmosphere into space using electromagnetic or physical methods. 2. Cooling the surface. Lowering the temperature is essential for habitability. Solar shades. Giant mirrors or shades positioned at Venus Lagrange point could block sunlight, cooling the planet over time. Chemical reactions. Introducing elements like magnesium or calcium could bind with atmospheric CO2, forming stable compounds. 3. Introducing oxygen and water. To support life, Venus would need water sources and breathable air. Hydrogen importation. Colliding Venus with hydrogen-rich asteroids or redirecting hydrogen from gas giants could react with CO2 to form water. Photosynthesis. Introducing extremophiles capable of surviving Venus conditions could gradually produce oxygen. Long-term implications. Terraforming would take centuries or millennia, depending on technological advancements and the scale of interventions. Even then, maintaining habitability would require continuous effort, as planetary systems might not stabilize naturally. Ethical considerations. Terraforming raises significant ethical questions. Environmental impact. Should humanity alter other worlds, potentially destroying native ecosystems or microbial life? Resource allocation. Given the immense cost and time, should resources be prioritized for Earth's challenges instead? Ownership and governance. Who decides how a planet is terraformed and who controls its resources? The future of terraforming. While the concept remains speculative, technologies developed for terraforming could have immediate applications. In situ resource utilization. ISRU techniques for extracting water and gases on other planets can support near-term missions. Climate engineering. Insights from terraforming research could help address climate challenges on Earth. Terraforming beyond the solar system. As humanity expands into the galaxy, terraforming may extend to exoplanets. Worlds with Earth-like conditions in the habitable zones of other stars might require only minor modifications. Advances in propulsion and energy technologies will determine how feasible these projects become. The path ahead. Terraforming represents the ultimate challenge in planetary engineering, blending physics, biology, and ethics into a single grand endeavor. Whether humanity undertakes this task or focuses on adapting to existing environments, the lessons learned will reshape our understanding of life, sustainability, and our role in the cosmos. How physics shapes mission design. Every space mission, from the smallest satellite deployment to the most ambitious interplanetary voyage, is an intricate ballet choreographed by the principles of physics. From the launch pad to final destination, mission design depends on a profound understanding of motion, energy, and the forces that govern the universe. But how does physics shape mission planning? And how do engineers and scientists leverage its principles to overcome the challenges of space travel? The foundations of mission design. Physics dictates every aspect of space exploration, starting with the fundamental laws of motion and gravity. 1. Newton's laws of motion. These laws form the basis for understanding propulsion, trajectory, and orbital mechanics. For example, Newton's first law explains why spacecraft in motion continue indefinitely in the vacuum of space unless acted upon by an external force. Newton's second law, F equals math equals ma, is central to designing propulsion systems, where force depends on the mass of the spacecraft and the acceleration required. Newton's third law, action and reaction, underpins rocket propulsion, where expelling fuel generates thrust. 2. The law of universal gravitation. Gravity governs the movement of celestial bodies and spacecraft. Mission planners use it to calculate orbital paths, escape velocities, and gravity assists. 3. Conservation laws. The conservation of energy and momentum ensures that fuel, speed, and trajectory adjustments are calculated with precision. Designing for launch. Overcoming gravity. The first challenge in any mission is escaping Earth's gravitational pull. Achieving this requires reaching escape velocity, approximately 11.2 kilometers per second, 40,270 kilometers per hour. The process involves rocket staging. Multi-stage rockets shed mass as fuel is expended, maximizing efficiency. Each stage operates under the Tsiolkovsky rocket equation, which quantifies the velocity change achievable based on fuel and mass ratios. Thrust-to-weight ratio. The thrust generated by the rocket must exceed the gravitational force acting on its mass. Engineers optimize engines to provide sufficient thrust while minimizing weight. Orbital mechanics, the art of placement. Once in space, mission design revolves around precise orbital calculations. Orbits are determined by the spacecraft's velocity and the gravitational pull of the central body, e.g., Earth, the Moon, or the Sun. Key orbital parameters include altitude. Higher orbits require more energy, but offer broader observational coverage. Inclination. The tilt of the orbit relative to a planet's equator determines coverage areas. Polar orbits, for example, enable global mapping as the planet rotates beneath the satellite. Eccentricity. The shape of the orbit, circular or elliptical, affects mission objectives, such as maintaining consistent proximity to a target. For interplanetary missions, engineers employ advanced techniques such as 1. Home and transfer orbits. These energy-efficient trajectories involve transitioning between two circular orbits using two carefully timed engine burns. 2. Gravity assists. By flying close to a planet, a spacecraft can gain or lose speed through gravitational interactions, reducing fuel requirements. For instance, the Voyager missions used gravity assists from Jupiter and Saturn to reach the outer planets. Propulsion systems, balancing efficiency and power. Choosing the right propulsion system is crucial for achieving mission objectives. Different propulsion methods cater to varying needs. Chemical rockets. provide high thrust for launching and quick maneuvers but consume fuel rapidly. Ion propulsion offers high efficiency for long-duration missions by expelling ions at high speeds, ideal for deep space exploration. Solar sails use the momentum of photons to generate thrust, requiring no fuel, making them suitable for interstellar probes. Mission designers calculate the delta-v budget, the total velocity change required for all mission phases, to determine fuel needs and propulsion system capabilities. Navigating the space environment. Space is not empty. It is filled with radiation, micrometeoroids, and the gravitational influences of celestial bodies. Physics plays a critical role in mitigating these hazards. 1. Radiation shielding. Protecting electronics and humans from cosmic rays and solar radiation involves understanding particle interactions and designing effective shielding. 2. Microgravity. In the absence of significant gravitational forces, materials behave differently. Engineers account for fluid dynamics, thermal transfer, and structural stresses in microgravity environments. 3. Orbital decay. Low Earth orbit missions must account for atmospheric drag, which can cause gradual orbital decay. Reboost maneuvers counteract this effect. Mission phases and physics. Each phase of a mission involves specific physical challenges and solutions. 1. Launch and ascent. Atmospheric drag and gravity impose significant energy demands. Aerodynamic stability ensures the rocket follows its intended trajectory. 2. Orbital insertion. Spacecraft must achieve precise speeds and angles to enter the desired orbit. Engineers use control systems like gyroscopes and thrusters for fine-tuning. 3. Cruise phase. For interplanetary missions, gravitational forces and solar radiation pressure influence trajectories. Mid-course corrections ensure the spacecraft stays on target. 4. Encounter and descent. Landing on celestial bodies requires understanding surface gravity, atmospheric density, if present, and terrain. Techniques like aerobraking, using a planet's atmosphere to reduce speed, save fuel. 5. Return, if applicable. Re-entry into Earth's atmosphere involves intense heat due to friction. Heat shields dissipate energy, protecting the payload. Mission design for specific objectives. 1. Earth observation satellites. Requires stable orbits with consistent sunlight, such as sun-synchronous orbits, to monitor environmental changes. 2. Planetary exploration. Complex trajectories and landers must be precisely designed to study distant worlds, such as NASA's Europa Clipper or ESA's JUICE mission to Jupiter's moons. 3. Deep space missions. For missions like Voyager or New Horizons, longevity and minimal fuel consumption are prioritized. Advanced tools and simulations. Mission design relies on sophisticated tools and simulations. Orbital simulators. Software like GMAT and STK models gravitational influences and spacecraft behavior. Computational fluid dynamics. CFD analyzes airflow and heat transfer during launch and atmospheric entry. Machine learning optimizes trajectories, autonomously adjusts navigation, and analyzes mission risks. Innovations in mission design. Emerging technologies are expanding the boundaries of mission design. 1. Reusable rockets. Companies like SpaceX are revolutionizing mission costs and flexibility with reusable stages. 2. 3D printed components, reducing weight and cost while improving structural efficiency. 3. Autonomous systems. AI-driven spacecraft can adapt to unforeseen challenges without waiting for Earth-based instructions. The future of mission design. Black holes and space travel. Black holes, among the most enigmatic objects in the universe, are both a source of fascination and a potential avenue for breakthroughs in space travel. These cosmic phenomena, with their intense gravitational pull and mysterious interiors, challenge our understanding of physics. While they pose significant dangers, black holes also offer unique opportunities for exploration, energy generation, and even speculative theories of interstellar travel. How might humanity harness these enigmatic objects? And what does their study reveal about the universe? What are black holes? A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. Black holes form from the remnants of massive stars that collapse under their own gravity, or through the merging of neutron stars or smaller black holes. They are characterized by singularity, a point of infinite density where all the mass of the black hole is concentrated. Event horizon, the boundary beyond which nothing can escape. Once crossed, all paths lead toward the singularity. Accretion disk, a swirling disk of matter heated to extreme temperatures as it spirals into the black hole. Types of black holes. 1. Stellar mass black holes, formed from collapsing stars. These have masses between 3 and 100 times that of the Sun. 2. Supermassive black holes, found at the centers of galaxies. These contain millions to billions of solar masses. 3. Intermediate mass black holes, rare objects with masses between stellar and supermassive black holes. 4. Primordial black holes, hypothetical black holes formed during the early universe, with masses ranging from subatomic particles to planetary scales. The physics of black holes. Black holes are governed by Einstein's general theory of relativity, which describes how massive objects distort space-time. Near a black hole, this distortion becomes extreme. Time dilation. Time slows down for an object approaching the event horizon relative to distant observers. Spaghettification. Intense tidal forces stretch and compress objects as they near the singularity. Hawking radiation, a quantum mechanical phenomenon where black holes emit particles, slowly losing mass over time. These properties make black holes unique laboratories for testing the limits of physics, particularly the relationship between general relativity and quantum mechanics. Black holes as energy sources. The immense energy associated with black holes has inspired theories about their potential use as power sources. 1. Accretion disk energy. Matter in the accretion disk heats to millions of degrees, radiating energy in the form of X-rays and gamma rays. Advanced civilizations could harness this radiation using massive energy-collecting structures, akin to Dyson spheres. 2. Hawking radiation. As black holes emit Hawking radiation, this energy could theoretically be captured. While the process is slow for large black holes, microscopic black holes could radiate more energy, offering a potential power source. 3. Penrose process. In the ergosphere, a region outside the event horizon of a rotating black hole, particles can gain energy by extracting angular momentum. This process could theoretically generate vast amounts of energy. Black holes and interstellar travel. The extreme properties of black holes have led to speculation about their use in interstellar travel. 1. Gravitational slingshots. Black holes' immense gravity could be used to slingshot spacecraft to high speeds, saving fuel and time. This technique, similar to gravity assist used with planets, would require precise navigation to avoid crossing the event horizon. 2. Wormholes. Some theories suggest that black holes could connect to other regions of space-time via wormholes, enabling faster-than-light travel. However, traversable wormholes would require exotic matter to stabilize, and their existence remains unproven. 3. Time dilation benefits. Time dilation near a black hole could allow long-duration missions to experience less elapsed time, making them suitable for exploring distant regions of the universe. However, re-entry into regions of normal space-time could result in centuries passing for the rest of humanity. Risks of black hole exploration. Despite their potential, black holes pose significant risks to spacecraft and astronauts. Tidal forces. Extreme differences in gravitational pull can destroy spacecraft approaching the event horizon. Radiation. Intense X-rays and gamma rays from the accretion disk can damage electronics and harm humans. Unpredictability. Black holes are dynamic and can merge or eject matter at high velocities, posing unpredictable hazards. Observing and studying black holes. Understanding black holes requires innovative observation techniques. Event Horizon Telescope, EHT. The EHT captured the first-ever image of a black hole shadow, providing direct evidence of these objects. Gravitational waves. Merging black holes generate ripples in space-time, detected by observatories like LIGO and Virgo, offering insights into their properties. High-energy observatories. X-ray and gamma-ray telescopes, such as Chandra and Fermi, study emissions from accretion disks and jets. The future of black hole research. 1. Microscopic black holes. If created in particle accelerators, these could provide a controlled environment for studying black hole physics and testing quantum theories. 2. Artificial black holes. Hypothetical technologies might one day create black holes for energy generation or propulsion. 3. Interstellar observatories. Advanced telescopes placed near black holes could exploit gravitational lensing to study distant galaxies and exoplanets. Philosophical implications. Black holes challenge our understanding of reality, raising profound questions about the nature of space, time, and existence. What lies beyond the event horizon? Could black holes lead to other universes or dimensions? What happens at the singularity? Understanding singularities could unlock a unified theory of physics. Are black holes gateways? Theoretical physicists speculate that black holes might serve as cosmic bridges, connecting different parts of the universe. Black holes as inspiration. While black holes remain one of the universe's greatest mysteries, they also represent humanity's drive to explore and understand. Their study pushes the boundaries of science, inspiring new technologies and insights that extend far beyond their gravitational pull. The future of space travel. As humanity ventures further into the cosmos, the future of space travel promises to be a blend of cutting-edge technology, ambitious exploration, and a profound redefinition of our place in the universe. From establishing permanent settlements on other planets to unlocking the secrets of interstellar travel, the road ahead is both exciting and challenging. What are the key trends, innovations, and goals shaping the next era of space exploration? Expanding beyond Earth. The first steps toward the future of space travel involve solidifying our presence in near-Earth space and gradually extending human activity to the Moon, Mars, and beyond. 1. Lunar colonization. The Moon serves as humanity's stepping stone into the solar system. Its proximity to Earth and abundance of resources make it an ideal testing ground for technologies needed for long-term space habitation. Artemis program. NASA's Artemis missions aim to establish a sustainable human presence on the Moon, with plans for lunar bases powered by solar energy and supplied through in-situ resource utilization, ISRU. Lunar Gateway. A space station orbiting the Moon will serve as a hub for research, logistics, and missions to deeper space. 2. Mars exploration. Mars represents humanity's next frontier. Its similarities to Earth, including a day length of 24.6 hours and evidence of past water, make it the most viable candidate for colonization. Crewed missions to Mars. NASA and SpaceX are developing technologies for sending humans to Mars within the next 2 decades. These missions will test life support systems, radiation shielding, and closed-loop ecosystems. Terraforming Mars. While speculative, terraforming could make Mars more hospitable by thickening its atmosphere and warming its surface. 3. Asteroid mining and space resources. Mining asteroids for metals, water, and other resources could fuel space travel and enable off-world economies. Near-Earth asteroids, NEA's robotic missions will extract valuable materials, reducing reliance on Earth-based supplies. Cislunar economy. A network of mining and manufacturing operations in the space between Earth and the Moon could support lunar and Martian colonies. Revolutionary technologies. The future of space travel hinges on breakthroughs in propulsion, energy, and life support systems. 1. Advanced propulsion systems. Traditional chemical rockets are insufficient for deep space exploration. New propulsion technologies will enable faster, more efficient travel. Nuclear thermal propulsion offers higher efficiency than chemical rockets, reducing travel time to Mars and beyond. Ion drives and electric propulsion. These systems are ideal for long-duration missions, offering high efficiency with minimal fuel consumption. Fusion propulsion. If achieved, fusion propulsion could enable interstellar missions by providing immense energy with minimal fuel. Light sails. Powered by lasers or sunlight, light sails could propel spacecraft to significant fractions of the speed of light, as envisioned by projects like Breakthrough Starshot. 2. Energy innovations. Reliable energy sources are critical for long-term missions. Space-based solar power. Collecting sunlight in space and transmitting it to Earth or other celestial bodies via microwaves. Nuclear reactors. providing consistent power for habitats, mining operations, and spacecraft propulsion. 3. Life support and bioregenerative systems. Closed-loop ecosystems that recycle air, water, and nutrients are essential for sustaining human life on long-duration missions. Aquaponics and hydroponics. Growing food in controlled environments to supplement supplies. Bioengineered microbes. Using microbes to process waste and generate essential resources like oxygen and fuel. 4. Artificial gravity. Long-term exposure to microgravity affects human health. Rotating habitats or spacecraft with centrifugal force will simulate gravity, mitigating muscle and bone loss. Interstellar exploration. The ultimate goal of space travel is reaching other star systems, a challenge that demands revolutionary technologies and unprecedented collaboration. 1. Proxima Centauri and Alpha Centauri. These nearby stars, located just over 4 light-years away, are prime targets for interstellar probes. Projects like Breakthrough Starshot aim to send tiny, light sail-equipped spacecraft to these systems, achieving speeds up to 20% of the speed of light. 2. Generation ships. For missions to distant stars, multi-generational spacecraft could house self-sustaining communities. These ships would require closed-loop ecosystems, robust energy sources, and artificial gravity. 3. Wormholes and warp drives. While speculative, breakthroughs in theoretical physics could enable faster-than-light travel, making interstellar exploration more feasible. 4. Exoplanet colonization. With thousands of exoplanets discovered, some in the habitable zone of their stars, humanity may one day establish colonies beyond our solar system. The role of AI and robotics. Autonomous systems will play a central role in the future of space exploration. AI-powered navigation. Spacecraft will rely on AI to adapt to unforeseen challenges and optimize trajectories. Robotic exploration. Robots will perform high-risk tasks, such as drilling on asteroids or exploring subsurface oceans on moons like Europa. Human-robot collaboration. Advanced AI will support astronauts in decision-making, research, and habitat construction. International and private collaboration. The future of space travel depends on collaboration between nations, private companies, and international organizations. Space agencies. NASA, ESA, CNSA, and others are coordinating efforts to explore the Moon, Mars, and beyond. Private companies. Companies like SpaceX, Blue Origin, and Rocket Lab are driving innovation, reducing costs, and opening new markets. Global agreements. International treaties will ensure the equitable use of space resources and the peaceful development of off-world settlements. Philosophical and ethical considerations. As humanity extends its reach, profound questions arise. Planetary protection. How do we prevent contamination of extraterrestrial ecosystems? Equity and access. Who owns the Moon, Mars, or asteroids? How do we ensure that space exploration benefits all of humanity? Existential purpose. What does it mean to become an interplanetary species? How will this reshape human identity and culture? The vision ahead. The future of space travel is a testament to human ingenuity, resilience, and curiosity. It promises to unite science, technology, and imagination in ways that redefine what is possible. As we stand on the brink of a new era, the stars no longer seem unreachable. They beckon us to explore, learn, and dream. Where current research is headed. As humanity pushes the boundaries of space exploration, ongoing research is addressing the technical, scientific, and philosophical challenges of venturing deeper into the cosmos. The focus spans a wide range of disciplines, from propulsion and life sciences to planetary geology and astrophysics. Where is current research taking us, and how will it shape the next great leaps in space travel? Propulsion innovations. Developing faster, more efficient propulsion systems is one of the highest priorities in space exploration. Current research efforts include 1. Nuclear propulsion. Nuclear thermal rockets, NTRs. These systems use a nuclear reactor to heat hydrogen, producing thrust with higher efficiency than chemical rockets. NASA and DARPA are collaborating on NTR designs for crewed missions to Mars. Nuclear electric propulsion. NEP systems convert nuclear energy into electricity to power ion thrusters, ideal for long-duration deep space missions. 2. Solar sails and beamed energy. Projects like Breakthrough Starshot are exploring the use of high-power lasers to propel light sails to interstellar speeds. Research is focused on developing lightweight materials capable of withstanding extreme acceleration and heat. 3. Fusion propulsion. Fusion engines, such as those being developed by private companies like Helion Energy, promise immense power and efficiency. Research focuses on containing and sustaining fusion reactions in a space-ready reactor. 4. Plasma and ion drives. NASA's Advanced Electric Propulsion System, APS, is refining ion thrusters for high-efficiency, low-thrust missions. The goal is to enhance performance for missions to asteroids, Mars, and beyond. Life support systems. Long-duration missions require sustainable life support systems. Current research is advancing. Closed-loop ecosystems. Experiments like the European Space Agency's Melissa program are developing regenerative systems that recycle air, water, and nutrients using biological processes. Bioregenerative agriculture. Hydroponic and aquaponic systems are being tested to grow food in space, integrating plants into life support loops. Radiation protection. Materials and magnetic shielding technologies are being studied to protect astronauts from cosmic rays and solar radiation on Mars and deep space missions. Space habitats and construction. Building sustainable habitats is essential for long-term exploration and colonization. Current efforts include 3D printing technologies. NASA and ESA are exploring the use of in situ resources, such as lunar regolith or Martian soil, to construct habitats with robotic 3D printers. Inflatable modules. Lightweight, expandable habitats like Bigelow Aerospace's B330 are being developed for space stations and planetary bases. Underground habitats. Research into Martian lava tubes and lunar craters explores the potential for natural shelters that provide radiation protection. Planetary science and resource utilization. Understanding the composition and resources of celestial bodies is key to supporting future missions. Lunar resources. NASA's Viper rover will map water ice deposits at the Moon's poles to support the Artemis program. Mars sample return. Perseverance is collecting samples for a future mission that will return them to Earth, advancing our understanding of Martian geology and potential biosignatures. Asteroid mining. Companies like Planetary Resources and Deep Space Industries are researching technologies to extract metals and volatiles from near-Earth asteroids. Human health and adaptation. The physiological and psychological effects of space travel are active areas of research. Microgravity countermeasures. Studies on the ISS examine how exercise, nutrition, and pharmaceuticals mitigate muscle and bone loss. Radiation biology. NASA's Space Radiation Laboratory investigates the effects of cosmic radiation on DNA and cells, seeking protective strategies. Mental health support. Research into virtual reality, AI companions, and other tools aims to combat isolation and stress during long missions. Advanced robotics and AI. Robots and AI are expanding the scope of exploration and enhancing mission efficiency. Autonomous rovers. AI-driven rovers like Perseverance use terrain analysis to navigate and prioritize scientific objectives. AI and spacecraft. Systems like NASA's Deep Space Autonomous Navigation, AutoNav, enable probes to adjust their trajectories without human intervention. Humanoid robots. Projects like NASA's Valkyrie aim to develop robots capable of assisting astronauts in hazardous environments. Astrophysics and fundamental science. Space missions are driving discoveries about the universe's origins and nature. James Webb Space Telescope, JWST, is revolutionizing our understanding of exoplanets, galaxy formation, and the early universe. Gravitational waves. Observatories like LIGO and Virgo are refining techniques for detecting cosmic events such as black hole mergers. Dark matter and energy. Space-based experiments aim to unravel the mysteries of dark matter and dark energy, which make up most of the universe's mass and energy. Interstellar research. The dream of reaching other star systems is fueling speculative but serious research. Interstellar probes. Concepts like NASA's Interstellar probe propose missions to the heliosphere's edge and beyond, studying interstellar space. Breakthrough initiatives. Projects like Breakthrough Listen and Breakthrough Watch focus on detecting extraterrestrial signals and observing exoplanets. Wormholes and warp drives. While highly theoretical, physicists are exploring the mathematics of faster-than-light travel within general relativity and quantum physics frameworks. Sustainability and ethical considerations. Current research also addresses the long-term implications of space travel. Space debris management. Organizations like ESA's Clean Space Initiative are developing technologies to remove debris from orbit and design sustainable spacecraft. Planetary protection. Guidelines ensure missions avoid contaminating other worlds with Earth microbes or vice versa. Equitable resource use. Policies for sharing the benefits of space resources are being debated in forums like the United Nations Committee on the Peaceful Uses of Outer Space. Emerging collaborative efforts. Space exploration is increasingly global and inclusive. International Lunar Research Station. China and Russia are collaborating on a moon base, inviting other nations to participate. Commercial partnerships. Companies like SpaceX, Blue Origin, and Axiom Space are working with governments to expand access to space. Citizen science. Public involvement in projects like SETI at Home and Zooniverse helps process data and engage broader communities. The horizon ahead. Research in space travel is not just about solving technical problems. It's about redefining humanity's relationship with the cosmos. As we develop the tools and knowledge to reach farther and live longer in space, we are laying the groundwork for a future where exploration becomes a cornerstone of human civilization. The ultimate goals of humanity's journey into the cosmos. Space exploration is more than a technical or scientific endeavor. It is a pursuit that embodies humanity's deepest aspirations. From uncovering the origins of the universe to ensuring the survival of our species, the ultimate goals of venturing into the cosmos reflect a blend of curiosity, survival instinct, and a desire to transcend earthly limitations. What drives us to explore space, and what milestones define our journey into the vast unknown, ensuring the survival of humanity. One of the most compelling reasons for space exploration is the long-term survival of humanity. Earth, while hospitable now, is vulnerable to natural and human-made disasters. Planetary risks, asteroid impacts, supervolcanoes, and other catastrophic events pose existential threats to life on Earth. Environmental degradation, climate change, resource depletion, and overpopulation could strain Earth's ability to support humanity. Cosmic catastrophes. Events such as gamma-ray bursts or changes in the sun's life cycle are inevitable over astronomical timescales. Expanding into space offers a solution. 1. Interplanetary colonization. Establishing self-sustaining colonies on the Moon and Mars provides a backup for humanity in case of Earth-based disasters. 2. Interstellar expansion. Reaching other star systems would ensure humanity's survival beyond the lifespan of the Sun. Searching for life beyond Earth. The quest to find extraterrestrial life is one of the most profound motivations for space exploration. Key initiatives include 1. Exploring Mars. Missions like Perseverance and the Mars Sample Return aim to uncover evidence of past or present microbial life. 2. Investigating ocean worlds. Moons such as Europa, Enceladus, and Titan harbor subsurface oceans that may support life. Future missions will probe these environments for biosignatures. 3. Exoplanet surveys. The James Webb Space Telescope and upcoming missions like the European Extremely Large Telescope are identifying Earth-like planets and habitable zones. 4. SETI, Search for Extraterrestrial Intelligence. Projects like Breakthrough Listen are scanning the skies for signals from intelligent civilizations. Discovering life elsewhere would transform our understanding of biology, evolution, and humanity's place in the cosmos. Expanding knowledge and technology. Space exploration drives scientific discovery and technological innovation. 1. Understanding the universe. Missions to study black holes, dark matter, and cosmic evolution help unravel the universe's deepest mysteries. 2. Advancing technology. Space research has led to breakthroughs in materials science, robotics, AI, and medical technology, with applications on Earth. 3. Inspiring innovation. The challenges of space travel push humanity to develop solutions that benefit multiple fields, from sustainable energy to precision manufacturing, creating a multi-planetary civilization. The vision of becoming a multi-planetary species reflects a desire for growth and resilience. Key goals include: 1. Establishing lunar and Martian settlements. These colonies will serve as hubs for exploration, research, and industry. 2. Developing off-world economies. Mining asteroids for resources, manufacturing in microgravity, and creating space-based power stations could revolutionize industries. 3. Expanding cultural horizons. Space settlements will foster new cultures, perspectives, and ways of life, shaping humanity's evolution. Exploring the limits of human potential. Space exploration challenges humanity to transcend physical, mental, and societal boundaries. 1. Adapting to new environments. Living on other planets will test our ability to survive and thrive in alien conditions. 2. Uniting for a common goal. Space initiatives often bring nations and organizations together, fostering collaboration and shared purpose. 3. Redefining identity. As humans spread across the cosmos, our sense of identity and connection to Earth will evolve. Building a cosmic legacy. Exploration is driven by a desire to leave a lasting impact. By venturing into space, humanity seeks to: 1. Preserve knowledge. Space missions and settlements ensure the survival of Earth's history, culture, and achievements. 2. Create a permanent presence. By establishing footholds on other worlds, we ensure that humanity's story continues for millennia to come. Ethical and philosophical dimensions. The ultimate goals of space exploration also raise important questions. 1. Planetary protection. How do we balance the desire to explore with the responsibility to protect alien ecosystems? 2. Equity in space. Who benefits from space exploration? How can we ensure that its opportunities and resources are shared fairly? 3. The meaning of exploration. What does it mean to explore? How does venturing into the cosmos shape our understanding of existence? The vision of the future. Humanity's journey into the cosmos is a story of transformation. Each mission, innovation, and discovery brings us closer to realizing a future where space is not just a destination, but a part of everyday life. The ultimate goals of space exploration are not merely technological or scientific, they are deeply human, reflecting our drive to understand, survive, and create. As we stand on the threshold of this new era, the stars remind us of the infinite possibilities ahead. The journey into space is not just a quest for knowledge. It is a testament to humanity's resilience, creativity, and enduring hope. The ultimate frontier, unifying humanity through space exploration. As humanity takes its first steps into the cosmos, space exploration emerges not just as a technical or scientific endeavor, but as a force for unifying people across the globe. The challenges of exploring space, building advanced technologies, addressing existential risks, and navigating ethical dilemmas demand collaboration, innovation, and shared vision. What role does space exploration play in bringing humanity together, and how might it shape a collective future? A shared vision for the future. Space exploration inspires a sense of wonder and possibility that transcends national, cultural, and political boundaries. Key elements of this shared vision include: 1. Discovering our cosmic origins. The quest to understand the universe's beginnings and the conditions that gave rise to life connects humanity to a larger story. 2. Securing humanity's survival. Ensuring a future for humanity by becoming a multi-planetary species is a goal that unites diverse perspectives and priorities. 3. Expanding knowledge and innovation. The pursuit of space exploration benefits all of humanity through technological advancements and scientific discoveries. Collaborative efforts in space exploration. International partnerships are a cornerstone of modern space exploration. 1. The International Space Station, ISS. The ISS represents one of the most successful examples of global collaboration, with contributions from over 15 countries. It serves as a platform for scientific research, technology testing, and cultural exchange. 2. Artemis Accords. These agreements set the framework for peaceful and cooperative exploration of the Moon and beyond, fostering collaboration between government and private entities. 3. Joint missions. Projects like the James Webb Space Telescope and Mars exploration involve partnerships between space agencies such as NASA, ESA, and CSA, pooling resources and expertise. The role of private industry. Private companies are playing an increasingly prominent role in space exploration, democratizing access to space and accelerating innovation. 1. Space tourism. Companies like SpaceX, Blue Origin, and Virgin Galactic are opening space to civilians, making it more accessible to diverse groups. 2. Commercial launch services. Private firms are reducing the cost of launching payloads, enabling more countries and organizations to participate in space exploration. 3. Public-private partnerships. Collaborations between governments and industry, such as NASA's partnership with SpaceX for crewed Mars missions, are driving progress. Cultural and philosophical impact. Space exploration has a profound cultural and philosophical impact, shaping how humanity views itself and its place in the universe. 1. The overview effect. Astronauts often describe a transformative experience when seeing Earth from space, a realization of the planet's fragility and interconnectedness. 2. Art and expression. Space has inspired art, literature, and music that reflect humanity's aspirations and curiosity. 3. Redefining identity. As humans live and work on other planets, our sense of identity and connection to Earth will evolve. Ethical considerations. Exploring space raises important ethical questions that require collective deliberation. 1. Planetary protection. How do we prevent contamination of other worlds while exploring them? 2. Resource use. Who has the right to extract and use resources from celestial bodies? 3. Inclusivity. How can space exploration benefit all of humanity, not just a select few? Space is a platform for global unity. Space exploration provides a unique opportunity to address global challenges. 1. Earth observation. Satellites monitor climate change, natural disasters, and resource management, supporting efforts to protect the planet. 2. Technological innovation. Space research drives advances in energy, communications, and transportation, contributing to sustainable development. 3. Diplomatic collaboration. Joint missions foster dialogue and cooperation between nations, promoting peace and understanding. The future of a unified humanity. As humanity ventures further into space, the vision of a unified global civilization becomes increasingly tangible. 1. Interplanetary society. Colonizing the Moon, Mars, and beyond will require shared governance, resources, and expertise. 2. Cosmic perspective. Understanding our place in the universe may inspire greater humility, cooperation, and a commitment to solving Earth's challenges. 3. A new era of exploration. Space is not just the next frontier. It is a catalyst for uniting humanity in the pursuit of a shared destiny. The road ahead. The ultimate frontier is not merely physical. It is a journey of the human spirit. As we explore the cosmos, we are also exploring what it means to be human, our capacity for curiosity, resilience, and collaboration. Space exploration offers a path toward unity, reminding us that while we may come from different places, we share one home, one future, and one universe. The ethical horizon of space exploration. As humanity ventures into space, the ethical dimensions of exploration and colonization come to the forefront. The decisions made today will shape how we engage with the cosmos for generations to come. How do we balance ambition with responsibility? And what principles should guide humanity's actions as we expand beyond Earth? Respecting extraterrestrial environments. Exploring other planets and moons comes with the responsibility of preserving their natural states. 1. Planetary protection. International guidelines, such as those set by the Committee on Space Research, COSPER, aim to prevent contamination of celestial bodies with Earth microbes and vice versa. These measures are particularly critical for missions to Mars, Europa, and Enceladus, which could harbor life. 2. Environmental ethics. As we extract resources or build habitats on other worlds, we must consider the ecological impact. Is it ethical to terraform Mars or mine asteroids without fully understanding their histories and potential ecosystems? Equitable access and benefits. Space exploration raises questions about who has the right to explore, colonize, and profit from the cosmos. 1. Space as a global commons. The Outer Space Treaty of 1967 declares space as the province of all mankind, ensuring that exploration benefits all humanity, not just a select few nations or corporations, is essential. 2. Resource sharing. Asteroid mining and lunar resource extraction could generate immense wealth. Developing frameworks for fair distribution is critical to avoid exacerbating inequalities on Earth. 3. Inclusivity in space exploration. Efforts must be made to ensure that all nations, regardless of economic status, have a voice in space policy and access to space technology. Ethical treatment of spacefarers. As humans venture deeper into space, ethical considerations extend to the well-being of astronauts and colonists. 1. Health and safety. Long-duration missions expose astronauts to radiation, microgravity, and psychological stress. Ensuring their safety and well-being is a moral imperative. 2. Autonomy in space colonies. Colonists on Mars or the Moon may develop distinct identities and governance structures. Respecting their autonomy while maintaining ties to Earth raises complex ethical questions. Interactions with extraterrestrial life. If life is discovered elsewhere, the implications would be profound. 1. Preserving alien ecosystems. If microbial or intelligent life is found, humanity must prioritize preservation over exploitation. 2. Ethical frameworks for contact. Establishing protocols for interacting with extraterrestrial civilizations, should they exist, is essential. Questions of communication, cultural exchange, and mutual respect will take center stage. Addressing space militarization. The increasing use of space for military purposes presents ethical and security concerns. 1. Preventing weaponization. The deployment of weapons in space could escalate conflicts on Earth and threaten global security. 2. Protecting critical infrastructure. Satellites are vital for communication, navigation, and weather forecasting. Safeguarding them from interference or attack is a shared responsibility. Sustainability in space. As humanity expands into the cosmos, sustainability must remain a core principle. 1. Reducing space debris. Thousands of defunct satellites and fragments pose a growing hazard to active missions. Developing technologies to clean up orbital debris is an ethical and practical necessity. 2. Sustainable resource use. Extracting resources from asteroids or planets must be balanced with the need to preserve them for future generations. Philosophical considerations. Space exploration forces humanity to confront profound questions about existence and responsibility. 1. Why explore? Is the primary goal of space exploration scientific discovery, survival, or something more existential? 2. Humanity's role in the universe. As stewards of Earth and potential shapers of other worlds, what responsibilities do we bear? 3. The search for meaning. The act of exploring space is not just about reaching new frontiers, but understanding humanity's place in the cosmos. Building ethical frameworks. As space exploration accelerates, proactive steps are needed to address its ethical dimensions. 1. Global governance. Strengthening international agreements, such as the Outer Space Treaty, to address modern challenges like resource extraction and private sector involvement. 2. Ethical advisory panels, including ethicists, scientists, and cultural representatives in decision-making processes for major missions. 3. Public engagement, ensuring that the global population has a voice in shaping space policy through education, dialogue, and inclusive initiatives. A legacy for the cosmos. The ethical horizon of space exploration is not just about what humanity achieves, but how we achieve it. By approaching the cosmos with humility, respect, and foresight, humanity can create a legacy that honors the shared values of discovery, stewardship, and unity. Humanity's role in shaping the cosmic future. As humanity ventures into space, our actions will influence not only the trajectory of exploration, but also the legacy we leave in the cosmos. The decisions we make, technologies we develop, and philosophies we embrace will shape the future of interplanetary and interstellar civilizations. What is humanity's role in the grand cosmic narrative, and how can we ensure it is one of discovery, stewardship, and progress? Becoming stewards of the cosmos. Humanity's entry into space comes with a profound responsibility to act as stewards of the universe. 1. Preserving cosmic heritage. Celestial bodies like the Moon, Mars, and Europa hold clues to the history of the solar system. Protecting these sites for scientific research ensures that future generations can continue to learn from them. 2. Balancing exploration with preservation. As we extract resources or modify environments, we must weigh the benefits of exploration against the potential loss of natural or historical value. 3. Creating ethical frameworks. Stewardship requires guidelines that respect the intrinsic value of extraterrestrial environments, whether or not they host life. Expanding the human frontier. Space exploration is not just about reaching new destinations. It is about expanding what is possible for humanity. 1. Scientific frontiers. Missions to study exoplanets, black holes, and the origins of the universe will push the boundaries of knowledge. 2. Technological innovation. Developing advanced propulsion systems, artificial gravity, and life support technologies will enable humanity to thrive in environments far from Earth. 3. Cultural evolution. Space settlements will foster new ways of living, working, and thinking, shaping a diverse and adaptive human culture. The quest for interstellar exploration. The dream of reaching other star systems is a natural extension of humanity's exploratory spirit. 1. Targeting nearby stars. Proxima Centauri and Alpha Centauri remain the most accessible targets for interstellar probes. Missions like Breakthrough Starshot are laying the groundwork for exploring these systems within the next century. 2. Interstellar civilizations. Establishing self-sustaining colonies in other star systems could transform humanity into a species that exists across the galaxy. 3. Challenges of interstellar travel. Overcoming vast distances will require breakthroughs in physics, propulsion, and energy generation. The pursuit of these technologies will redefine human ingenuity, creating a multiplanetary society. The development of a multiplanetary civilization is central to humanity's long-term survival and growth. 1. Lunar and Martian habitats. Initial settlements will serve as test beds for self-sustaining systems and interplanetary governance. 2. Asteroid mining and industry. Utilizing the resources of the solar system will create new economies and reduce reliance on Earth's limited resources. 3. Terraforming. While controversial, transforming Mars or other celestial bodies into habitable environments may one day become feasible, enabling large-scale human migration. Uniting humanity through space exploration. Space has the power to unite humanity in pursuit of common goals. 1. Global collaboration. International partnerships on projects like the International Space Station and Artemis program demonstrate the potential for cooperation across nations. 2. Shared challenges. Addressing the technical, ethical, and logistical hurdles of space exploration requires collective effort, fostering a sense of global solidarity. 3. A universal perspective. Viewing Earth from space inspires the overview effect, a profound realization of the planet's fragility and interconnectedness. This perspective can motivate humanity to work together to address global challenges. The search for extraterrestrial life. The discovery of life beyond Earth would fundamentally alter humanity's understanding of its place in the universe. 1. Microbial life. Finding microbial life on Mars, Europa, or Enceladus would confirm that life is not unique to Earth and raise questions about its origins. 2. Intelligent civilizations. Detecting extraterrestrial intelligence would challenge our assumptions about consciousness, technology, and communication. 3. Ethical interactions. If humanity encounters intelligent life, developing respectful and mutually beneficial relationships will be paramount. Challenges and risks. Humanity's expansion into space is fraught with risks that require careful navigation. 1. Resource conflicts. Competition over lunar or asteroid resources could lead to geopolitical tensions if not managed cooperatively. 2. Space militarization. The use of space for military purposes threatens the peaceful development of the cosmos. 3. Cultural fragmentation. As space colonies develop unique identities, maintaining unity with Earth and other settlements may become a challenge. Inspiring future generations. Space exploration is a source of inspiration for people of all ages, encouraging the pursuit of science, technology, and creativity. 1. Education and outreach. Engaging young minds with the wonders of space fosters a new generation of explorers and innovators. 2. Public participation. Citizen science initiatives, virtual missions, and space tourism make space exploration accessible to everyone. 3. Cultural expression. Art, literature, and media inspired by space exploration deepen humanity's connection to the cosmos. Humanity's legacy in the universe. As we explore space, we are not just seeking knowledge but creating a legacy that reflects our values and aspirations. 1. Ensuring continuity. Building self-sustaining colonies ensures that humanity's story continues even in the face of Earth-based challenges. 2. Contributing to the cosmos. By exploring and understanding the universe, humanity becomes an active participant in its evolution. 3. Embracing responsibility. Our actions in space will define how future generations view humanity's role in the cosmos. The call to explore. Space exploration is more than a technological endeavor. It is a testament to humanity's courage, curiosity, and resilience. It challenges us to dream beyond what seems possible, to work together for a shared future, and to embrace the unknown with hope and determination. As humanity takes its first steps into the cosmos, the ultimate question is not just where we will go, but who we will become. The stars are not just destinations. They are a call to rise above our limits and create a future worthy of the infinite possibilities before us. Humanity's role in shaping the cosmic future. As humanity ventures into space, our actions will influence not only the trajectory of exploration, but also the legacy we leave in the cosmos. The decisions we make, technologies we develop, and philosophies we embrace will shape the future of interplanetary and interstellar civilizations. What is humanity's role in the grand cosmic narrative, and how can we ensure it is one of discovery, stewardship, and progress? Becoming stewards of the cosmos. Humanity's entry into space comes with a profound responsibility to act as stewards of the universe. 1. Preserving cosmic heritage. Celestial bodies like the Moon, Mars, and Europa hold clues to the history of the solar system. Protecting these sites for scientific research ensures that future generations can continue to learn from them. 2. Balancing exploration with preservation. As we extract resources or modify environments, we must weigh the benefits of exploration against the potential loss of natural or historical value. 3. Creating ethical frameworks. Stewardship requires guidelines that respect the intrinsic value of extraterrestrial environments, whether or not they host life. Expanding the human frontier. Space exploration is not just about reaching new destinations. It is about expanding what is possible for humanity. 1. Scientific frontiers. Missions to study exoplanets, black holes, and the origins of the universe will push the boundaries of knowledge. 2. Technological innovation. Developing advanced propulsion systems, artificial gravity, and life support technologies will enable humanity to thrive in environments far from Earth. 3. Cultural evolution. Space settlements will foster new ways of living, working, and thinking, shaping a diverse and adaptive human culture. The quest for interstellar exploration. The dream of reaching other star systems is a natural extension of humanity's exploratory spirit. 1. Targeting nearby stars. Proxima Centauri and Alpha Centauri remain the most accessible targets for interstellar probes. Missions like Breakthrough Starshot are laying the groundwork for exploring these systems within the next century. 2. Interstellar civilizations. Establishing self-sustaining colonies in other star systems could transform humanity into a species that exists across the galaxy. 3. Challenges of interstellar travel. Overcoming vast distances will require breakthroughs in physics, propulsion, and energy generation. The pursuit of these technologies will redefine human ingenuity, creating a multiplanetary society. The development of a multi-planetary civilization is central to humanity's long-term survival and growth. 1. Lunar and Martian habitats. Initial settlements will serve as test beds for self-sustaining systems and interplanetary governance. 2. Asteroid mining and industry. Utilizing the resources of the solar system will create new economies and reduce reliance on Earth's limited resources. 3. Terraforming. While controversial, transforming Mars or other celestial bodies into habitable environments may one day become feasible, enabling large-scale human migration. Uniting humanity through space exploration. Space has the power to unite humanity in pursuit of common goals. 1. Global collaboration. International partnerships on projects like the International Space Station and Artemis program demonstrate the potential for cooperation across nations. 2. Shared challenges. Addressing the technical, ethical, and logistical hurdles of space exploration requires collective effort, fostering a sense of global solidarity. 3. A universal perspective. Viewing Earth from space inspires the overview effect, a profound realization of the planet's fragility and interconnectedness. This perspective can motivate humanity to work together to address global challenges. The search for extraterrestrial life. The discovery of life beyond Earth would fundamentally alter humanity's understanding of its place in the universe. 1. Microbial life. Finding microbial life on Mars, Europa, or Enceladus would confirm that life is not unique to Earth and raise questions about its origins. 2. Intelligent civilizations. Detecting extraterrestrial intelligence would challenge our assumptions about consciousness, technology, and communication. 3. Ethical interactions. If humanity encounters intelligent life, developing respectful and mutually beneficial relationships will be paramount. Challenges and risks. Humanity's expansion into space is fraught with risks that require careful navigation. 1. Resource conflicts. Competition over lunar or asteroid resources could lead to geopolitical tensions if not managed cooperatively. 2. Space militarization. The use of space for military purposes threatens the peaceful development of the cosmos. 3. Cultural fragmentation. As space colonies develop unique identities, maintaining unity with Earth and other settlements may become a challenge. Inspiring future generations. Space exploration is a source of inspiration for people of all ages, encouraging the pursuit of science, technology, and creativity. 1. Education and outreach. Engaging young minds with the wonders of space fosters a new generation of explorers and innovators. 2. Public participation. Citizen science initiatives, virtual missions, and space tourism make space exploration accessible to everyone. 3. Cultural expression. Art, literature, and media inspired by space exploration deepen humanity's connection to the cosmos. Humanity's legacy in the universe. As we explore space, we are not just seeking knowledge, but creating a legacy that reflects our values and aspirations. 1. Ensuring continuity. Building self-sustaining colonies ensures that humanity's story continues even in the face of Earth-based challenges. 2. Contributing to the cosmos. By exploring and understanding the universe, humanity becomes an active participant in its evolution. 3. Embracing responsibility. Our actions in space will define how future generations view humanity's role in the cosmos. The call to explore. Space exploration is more than a technological endeavor. It is a testament to humanity's courage, curiosity, and resilience. It challenges us to dream beyond what seems possible, to work together for a shared future, and to embrace the unknown with hope and determination. As humanity takes its first steps into the cosmos, the ultimate question is not just where we will go, but who we will become. The stars are not just destinations. They are a call to rise above our limits and create a future worthy of the infinite possibilities before us. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.